Yeah, that's not plugged in yet.
Oh. Let's see if that works. All right. Good morning, everyone. We're going to have the 4C team here trying to do some technical updates so that we can do some live training on the device. Helps a little bit with doing understanding the technology, understanding quantification, when you can kind of show the examples that they have, and also kind of help show some of the challenges in, some of the problems that you may run into and some of the roadblocks and the call outs for using the device. So hopefully they will get that done, but we've got a couple hours before that happens. So I'm gonna grab a water real quick. Still early for me. I may step away from this mic. Can y'all hear me in the back okay without the mic? All right. Well, I appreciate you coming here. My name is Craig O'Neill. Those of you that may not have met me, I'm with FLIR, Teledyne FLIR now. So for those of you that don't know about FLIR, we just recently were acquired this year. So we're still getting into our new normal there. And so I've been with FLIR for 20 years, and I've actually been directly involved in optical gas imaging since the inception of optical gas imaging by FLIR in 2005 with the world's first commercial infrared, commercial optical gas imaging camera. So been doing this for a little bit and directly involved in this. But throughout that entire time, and really soon after our first optical gas imaging camera, our partner in Providence, Photonics, came to us and said, you know what, this is going to be our life too, right? So this has been my life for the last 15 plus years. And our partners with Providence Photonics said, okay. Oh, for the recording. Yeah. Oh, no problem. So our partners at Providence came in and said, this is going to be our life as well. And they've been a great partner for the majority of that time on this ride. And in 2019, and I'll talk a little bit of this in the presentation, 2019, we entered into a formal partnership with Providence. The reason I say that is joining me today is Yoshing Zing, who is with Providence Photonics. He's going to talk a little bit on the actual engineering, the back end, the nuts and bolts of the quantification algorithm and the solution. And I'm going to kind of get into the over-encompassing training for QOGI and the QL320 itself. I don't know if there's specific breaks, so I'll try to we'll take breaks. I don't know if there's exact break times. It's just said 4 hours, so I hope you understand. I'm not going to stand here and talk for 4 straight hours, but I probably could. Most people that know me. So what we're going to kind of go in, I do want to introduce everyone to the actual device itself and to the technology, the QOGI technology. In doing that, there are the basic fundamentals. Again, we're going to try to keep this as least technical as we can. The goal of this is really to introduce everybody to QOGI but get into some of the technical aspects of QOGI, some of the call outs and some of the potential challenges in utilizing the technology. We will get into the actual method of the QOGI, which I'll introduce that, and then Yoshing will come up and actually get into those of you that might be interested in a little bit more of the technical background. Yoshing's going to get in to some of the theoretical foundation and some of the new stuff that they're utilizing, similar to with the QOGI technology, with utilizing the optical gas imaging camera for detection limits. To try to help it in explaining some of the potential future of optical gas imaging as it relates to establishing detection limits within the technology. We're going to get into learning the QL320 itself. And so that's where hopefully, and I will charge this up here in just a second, but we're going to get into learning the device. And I'm going to, the good thing about this is once you can get it set up, which is the hard part, a lot easier in today's world. You just get on a Zoom call and you connect with that. So once you can get it set up to connect to a projector, it's really easy. And the team at Providence did a great job of setting this up and allowing a very simple, easy, and basic way to demonstrate. But if you can demonstrate it easily, you can also train on it. I do want to get into the tips and tricks because it's not simply point and shoot. It's not go out there and look. There are some call outs that you need to understand in utilizing QOGI. The method limits and performance and what this is going to be. And Yoshing may get up and talk a little bit about some of the studies that they have done over the years to try to understand, how it works, but also to try to get industry guidance and industry acceptance through various coalitions and various organizations that they've partnered with. And this says questions and discussions at the end. Feel free to ask a question. This is going to be, again, 3 or 4 hours here, so we want to make sure that if you have questions, feel free to jot them down. Anytime you see me stop talking, if I can, feel free to ask a question. Keep it kind of intimate here if you'd like. But getting really directly into it, what is QOGI? The guy writing on the board there, that is the actual equation that the Providence team is using. I'll fully admit we're in a great partnership, but he knows all that equation and I don't. And I understand the basics of it, and he'll get into that a little bit better and simplify it and break it down. But in essence, all optical gas, the quantification, it's using a FLIR optical gas imaging camera, and specifically, this is going to be our cooled mid-wave hydrocarbon camera. So, when you see that, those of you that are familiar with FLIR, we have a full suite of optical gas imaging solutions, some newer uncooled, and some other long-wave optical gas imagers, if you will, a hydrocarbon camera that is going to be a cooled camera that you can utilize, giving you, with a unique and special algorithm, giving you the capabilities to quantify emissions or quantify what you're looking at with an OGI camera. When we get into this, a lot of the times, I like to get it out of the way first is why would somebody want to use a QOGI system? Why would they want to use an optical gas imaging quantification solution versus what else is in the industry? It is a newer technology compared to some of the other stuff, but with OGI, historically, it's been the top qualitative technology. Now, you can go out there and you can find the leaks, right? You can go look all you want and find needles in a haystack, but if you don't have the right tool to look for the needle, it's going to be very hard to find. And OGI is that right tool to look for needles in the haystack as it relates to emissions for hydrocarbons. And so when you're utilizing other devices, other technologies, they are limited in the capabilities. And the great thing, you don't know exactly where to point that technology unless you have an OGI camera going. With QOGI, you can simply point it there, and it's going to find the maximum leak rate. It's going to quantify that, and you're not going to need to be guessing. Are you pointing the device in the right area? So you know exactly what you're looking at. You know exactly. You can see the leak. You can see what's happening. What I like to define it is you have situational awareness of what's happening right in front of you when you're trying to quantify the solution, quantify the emission. The other one is the DTM component. When you're trying to find and quantify difficult to measure devices, there are a lot of technologies that are extremely limited in that. Either they just can't do it, or to do it, you might have to spend a week building scaffolding, having people drive into work, a couple people to spend an entire week to be able to have scaffolding to inspect an area that's full of difficult to measure components. With the QOGI solution, it'll actually quantify a component, emissions from a component up to about 100 feet away. And so when you're utilizing the technology, you just can simply walk in, look up, and actually effectively quantify an emission in something in an area that has been, if not difficult, impossible for the past X amount of years that the organization may have been using various technologies to do quantification. And so it's a really unique opportunity to be able to take a component like this, although this is not a QOGI because you can see it's not steady, but a component like this is an ideal component that is at a considerable distance away, and even to build scaffolding around all of that piping would be almost impossible to be able to get up to it. So it's a huge advantage of the quantification of optical gas imaging solution. And the other one is the accuracy. We're not going to sit here and say that we're as accurate as every other one. Part of the accuracy challenge with other technologies goes back to my first bullet point. If I don't know where to point it, I'm not ever going to be accurate. And so we've done multiple studies. When I say we, FLIR and mostly the Providence team have done studies. One of them we'll talk about later. It's called QOGI. In essence, in a directed sniffer, right? So a directed sniffer into this. When I say directed, that means we're even telling the sniffer where to go, right? They're utilizing the advantage of an OGI camera to find a leak, but in a directed sniffer, the QOGI solution, and this is also based on the original QOGI solution that's been advanced many times since the partnership with Providence and FLIR. In that solution, the QOGI, the QL100 or the QOGI solution was about 5 to 6 times more accurate to be able to quantify emissions than, if you will, at the time the method 21, the gold star for quantification of emissions in utilizing a TVA or a sniffer. So there is, and these are also, there were people on the advisory panel of this test and this study from the Power Five, the biggest, some of the top, this was in Europe, some of the top European oil and gas producers, as well as there were people here in Texas that I know, are with large oil and gas producers based in Texas that were in Europe and on the advisory council of this study. So really interesting, and when you start looking at some of the comparison, it's been pretty positive with respect to the QOGI and the QL at the time 100 and now the QL 320 solution. But when we look at it in basic terms on what is the QL 320, it is a specialized device. It's right now it's a tablet that it is a class 1 division 2 tablet. It's not, and so most of the time it's, you have to be wired in, and we'll talk about how you would use it with the FLIR camera later. But it's a ruggedized tablet that you can save, either save files on a camera or directly and immediately have a response through a tethered connection to the device to a camera. It will work with any of the GF series cameras that are hydrocarbon based and radiometric. And what we mean by that is a camera has to have the ability to measure temperature. So the GF320, the FLIR camera that's been out for many years, the GFX320, which is a class 1 division 2 hazardous location certified camera. Not only can it do that, we'll talk a little bit about the Q mode feature as well to show how you can do this in a class 1 div 2 area without needing to connect the devices together. And our GF620, our new high definition 640 infrared imager for optical gas imaging. As I mentioned, that the equation and the foundational stuff, that's the special sauce in the QL320 to allow it to do that. It's going to give you the capability to measure in common measurements and common units that are out there from your mass and your volume. And it's got, I don't believe, probably I think 8 to 10 different units. Whether you want grams per hour to equal a quad OA type of understanding of a leak size, or standard cubic foot per hour, which is most common probably here in the U.S. Standard cubic centimeters per minute, which when we get into EMEA and some of the outside the U.S. Areas. So you've got all of these different things, but one of the newer features in there is actual quantification in concentration. And so you will have a concentration over an assumed path length, so a parts per million meter measurement in the basics of operation of the QL320. And so that's a newer feature that's only been out for a couple of years. And so it's a really unique way to do that for those that are interested in more of that concentration type of reading. And then, as I mentioned, there's 2 ways to use this. So one way is allows you to get direct details and direct quantification while you're in the field on site. There are some advanced features which we'll talk about when we talk about the operation of a quantification device with the QL320. There are some of those advanced features on there that give you a little bit more flexibility in how it operates when you have it tethered. And that's the way it's historically been used. But when we entered into a partnership and we worked with Providence and said, realistically, when we launched our Class 1 Division 2, we had a lot of customers that said, you know what, I want to do this, but I can't do it in a Class 1 Div 2 because I have to open the camera and I have to open the actual QL320 device. And so at that time, we invented a feature called Q mode. And so what we're doing in the camera, if you have a camera that's manufactured from March 2019 and beyond, that's a GF320, X320, or a 620, it will have that feature built in. If it doesn't, we can get that feature loaded onto your camera with the purchase of the QL and have it upgraded. And so what in essence it's doing is we're storing a 20-second video that's in a proprietary FLIR format. And the Providence team has adjusted the QL320 to be able to take that that 20-second video and actually post-process it. So you don't have to be in the field tethered and connected to be able to use it with the Q mode feature. You can actually have the capabilities of quantifying at your leisure. Maybe you want to do every leak you find in an area. Maybe you only want to go back and see the ones that are a little bit larger in what you're trying to do. When we look at this, while, as I mentioned, this is a bit of a newer technology, it is on its third iteration. So in a short order, realistically in 5 years, we're in the third generation of the quantification solution. I know that the team at Providence, even pre-2016, they had been working on that for quite some time. And had more beta versions. But in 2016, they launched the very first yellow branded QL100, a much more basic. And since then, we've all learned a lot more, been able to add features like quantification through concentration and some other features, like a delta T overlay, which we'll talk a little bit about, that makes it visually understanding what's happening better. And then before we entered into a formal agreement in 2017, whenever I moved into this position at FLIR, I went to the Providence team and said, this is awesome, but we need this to kind of align with our camera lineup a little bit better. So we had the Providence brand in 2017, QL320, the original QL320, the blue QL320. And that's where we added the Q mode features and added some if you will, some user features to make it much more user friendly in the field. And then in 2000, and I believe it was 19 or 2020, after our minority share investment, our formal agreement with Providence, that's when we launched the FLIR QL320, where in the model that we have today. And what that was is from 2017 to 2020, we took feedback from you, right? The people in the field that were trialing this, go in a demo. What do you like? What do you not like? And we redid the entire user screen and added a handful or more features to try to make this more user friendly, to try to make this easier to use while you're out in the field, as well as when you're back in the office. So really great partnership with Providence and the evolution of that over time. What does it do and how does it work? There are some variables that we do, so you do have to input. And when you see the screen on the left side of the QL320, let's see if this works. Hey, right there, over here on the left side of the QL, there are some variables and inputs that you would need to put in. It's very basic, nothing challenging that you need to do. You need to choose the main, you need to choose, is the leak that you look at, is the leak that you see on the screen, is it black or white? We'll get into what that means in the training on whether it's an emissive or an absorptive plume. But is the leak black or white? You simply input what color you see. Not too challenging. I can even do that over the time. But you're going to add the input temperature. You're going to add the ambient air temperature of what it is, and that can be found with a thermo anemometer or something like that, or a piece of paper. And because the cameras are made to measure temperature, so you can actually just take a piece of paper and put it in front of the camera or something like that. Most people know the ambient air temperature, and it's going to change over time, but usually over a span of using the camera, it's going to be pretty consistent. You want to input your estimated distance. You'd like to get as accurate as you can. You can use a laser distance finder from FLIR or buy one from Bushnell that can also hunt deer, like most of the customers that I have do. And so you can utilize a laser distance meter to understand, you know, are you 20 feet or 26 feet? That distance does affect. So these inputs, all of that algorithm that you saw, all that formula you saw, all of these little inputs will change that a little bit. And now as you change everything a little bit, it begins to change it a lot. And so it's looking at that. And the way it realistically works is when it's measuring in mass or volume, right? Concentration's a little bit different. We'll talk a little bit about that. But when it's measuring mass or volume concentration readings, it's watching the pixels move from the center and it shows the exit velocity around that blue circle. So you have that's called a boundary here. That you can turn that on and off. But what it's doing is it's finding where the leak origins. You want to try to get the where the leak starts in the center of the screen, and it's seeing where it goes from the center of the circle or from inside the circle as it moves to the boundary on the outside of the circle. So the basics of how it works. It will work in all the environmental conditions that you need. So it makes it really easy and versatile to use in that way. And as we mentioned, you know, it will report that leak rate, a true mass volume or concentration leak rate. What do I need to use this? And this is where we start getting into the technology, how it works with the FLIR devices. You will have to have a FLIR camera to use the QL320 solution. And so, as I mentioned, many cameras from March 2019 and beyond have this technology in it to use, but you will need a FLIR camera. Another thing you'll need is a tripod. Now, as I mentioned, and I showed you a minute ago, as that leak moves from the center to the edge, the technology is actually watching a pixel by pixel movement, right? It's watching that leak move. And if I'm moving the camera, it doesn't know if I'm moving or if the leak's moving. And so the way the technology is developed today, you will need to stabilize the camera with a tripod. And we'll talk a little bit, is it tomorrow? I believe it's tomorrow, on some stuff that Providence is working on to actually minimize that feature. And so we'll talk a little bit about the future of the QOGI technology. The way it is set up today, you would need the tripod so that as those pixels move left, right to left, or up or down, you do that. The cabling, that's only if you're going to want it tethered. If you're going to want the live readings within the QL320, you would need to tether it in, and you'd have to have a cabling. We do recommend some sort, because you do need to know the wind speed. Now, it doesn't have to be super accurate wind speed. Now, ambient air temperature, we need you to be pretty accurate, and that's where this device is also a thermo anemometer, so it will measure both wind speed, but also the ambient air temperature, which is a huge advantage. You need something to be able to measure somehow the ambient air temperature, but the wind speed is pretty basic. It's 0 to 1, 2 to 10, or 10 and beyond. So there is a little bit of a fudge factor on the wind speed, you know, as far as accuracy goes. But you do need some way to input the ambient air temperature and then some sort of distance measurement device so that you can actually be as accurate as possible in establishing the distance, the distance that you are from the emission or from the leak. But what can you use it for, and what can you actually measure with this device? You know, any fugitive hydrocarbon emissions can be utilized in there. And as I mentioned, there are these various things that are either inputs personally through the previous devices and doing that. If it's, you know, there are two different ways to do it. There's a diffuse leak and a point leak. The point leak is going to be probably 95% or more, which means it starts from a small point and moves out, versus something that's more diffused, like a tank seal, where it's kind of leaking everywhere. So the majority of the leaks, LDAR leaks, that you would probably try to do with this are going to be a point leak. And so you can do that with point sources as long as the diameter of that is less than 12 inches, and to be able to do that. And I think the point leak is, I think it's a 3-inch diameter or something like that. As far as that, the majority of the time you're going to do this, you know, if you're looking at a Nardo valve or a vent stack or something, you know, you're going to be able to just use the point emissions. And realistically, I just put a list here, anything that leaks for the most part. We're working on tank seal emissions, and the Providence team is working with the EPA on trying to find a better solution. We'll talk a little bit about that tomorrow as well on the advancements of quantification breakout session. But realistically, if it emits hydrocarbons with this camera within the boundaries within 100 feet, flares is not really, as an example, not something that's really overly ideal for this as it relates to the technology, just mostly for the distance in you're trying to do there. And there's other technologies for flare, but anywhere that you see, if you will, a fugitive emission LDAR type of leak, this is going to be an ideal tool for quantification. So I want to get into kind of the fundamentals. Are there any questions about the basics while I take a sip of water? Yes, sir.
What is the government agency that concentration?
Yes. There is no requirement with QOGI right now to require, if you're using optical gas imaging in the US as a government agency, if you're using OGI, if it's a leak, it's a leak. I don't need a quantifier to do that. Both Canada and Mexico do accept the QL320 concentration path length parts per million meter reading as an acceptable use of quantification or acceptable means of quantification within the new Canadian regulations as well as the new Mexican regulations. We are working in a number of ways, a number of ways to do this. California is even behind the curve realistically against a lot of other states on acceptance of OGI as a technology in specific. But we are working with the EPA. They are evaluating the technology through their firm that they use to do evaluation of technologies for optical gas imaging. And we are working with the states directly, get them educated, in trying to get this technology to do that on the state level. I don't really know or anything of that. I would say that we're also working with the Providence team to make the technology easier to use, more user-friendly, so that acceptance for regulatory drive or just in industry in general will go up and be able to do that. So we are working and we're working a number of different avenues there.
Is that if you have a stable drone?
Not time. We have our drone solution, our GF320, which is the GF320 engine in a drone package. Then you're not implementing the quantification technology to the drone solution.
And on your handheld, I don't know, a bunch of points I have to record. It'll take all that and download it.
It's going to take each individual recording. At the way that it's set up today, it's going to take each individual recording and process those one at a time. The way it's set up today, and we're working with the engineering team as well to try to make that a little bit better user experience. Yeah.
All right, thanks.
Yep.
Just along.
I discussions a little bit, but more on the operators that want to have more accurate emissions inventory reporting. And we'll talk a little bit when we get into some of the studies that are done, and whether you take a larger subset of your stuff or you try to quantify individual one. The more you use this on an aggregate, and so we'll talk a little bit about that on some of the studies that are done. But I would say our problem operator side to do emissions inventory, also to do vent confirmation. If I have a pneumatic actuator, it's allowed to 6 standard cubic foot per hour, and a regulator comes in and says, well, that's leaking, it's bad, and you can go in and say scuff, then that helps us working with a number of people in that regard. But I've actually seen more of the operator side of the industry inventory. Yep. Yes, sir. That I believe Yoshing I think it's 100 feet with a 92mm with the highest end lens. With the standard lens, I believe it's up to about 50 feet, give or take for the 25 field of view lens. It's good. Correct. It could be farther. It could be. Well, the problem is we've all of users, and it. The longer out the ranges may have to change and kind of simplify the technology. 99% of the users going to use the scale of the calibration range. 2 calibration ranges per in this technology here in a little bit. It'll actually change the it'll change or it's bigger or smaller as the distance is. So at calibration range per lens. And so, yeah, you can add a new calibration range. The further out, you'd have to change the equation per se, because as you go out, you're actually and so we're just trying to I would say utilize it for the standard the most standard operators that we've seen over our experience in the last 5 years. It can just need to tweak that equation that you saw on the second. Yeah. Thank you. Oh, I'm sorry. Yeah. I don't know to answer that question off the top. Do you know that, Yoshing?
Basic question is if even if it's coronate, but it still have hydrocarbon bound in that compound, it's very likely it will be.
And it may not be as high of a response factor or as sensitive. So you would need to adjust. Yeah.
Yeah. It could go either way.
Mm-hmm.
Some of them are sensitive.
Correct. What can be detected. So and you do have to put in, one of the inputs you do put in is the primary gas. And right now, out of the box, the way that the solution is delivered, there are 8 to 10 standard, most common hydrocarbon gases that you would input as the primary gas within a stream. But it can be the technology, and the great thing working with Providence, that team, the technology can be adjusted to have much more. And you can even develop, if you know your stream within your facility is X percentage of this and X percentage of that, you can actually work with us and to be able to develop your own hydrocarbon, your own drop-down menu stream for the most common stuff within your process. All right, so how does it work? Kind of get into this, the basics of QOGI. Some of you, I guess I should have asked the question. I'm just curious now. How many of you use an OGI camera? So most everybody here. Does anybody utilize and have the quantification technology within your organization? So some new people to QOGI. So some of this, I never know, where the level is of understanding for just optical gas imaging, but the basic principles of how OGI works are the same foundational principles on how QOGI works, because they work in tandem, right? The QOGI technology is doing this. The way an OGI camera works, and the most basic way over the last 15 years I've found to do this is energy goes from an object into the camera, right? So if I look at my plant, whatever it is, and this is the common question that I've had for 16 years. Does the camera only see gas? Anybody know the answer to that question? You use a new OGI camera? No. I mean, I can see you, I can see the fittings, I can see the elbow. I see the gas coming out. The camera is engineered to be able to highlight the gas. But everything is going to emit energy in the same filtered spectrum. So everything's going to emit energy all across the electromagnetic wave band and infrared. So it's going to emit energy into the camera. But what happens is gas ends up getting between that emitted energy, that background object, and the camera itself. And it blocks some of that energy. So when you see the smoke, what's realistically happening, and most of the time, now when you're looking at the sky, it's a little bit different because energy, it's actually the lack of energy. And that's what we'll talk about in a black versus white plume, emissive versus absorptive plume here in a minute. But what happens is when you get the gas in between, shows and why the image looks like smoke, it is solely because we're blocking the camera from the capability. That gas is actually blocking the camera's capability to allow that background energy to get into the camera detector. And so it shows up kind of as smoke. Most of the time, realistically, it's showing up as smoke because we can't see it because we're blocking it out. We're leveraging that. And what we're doing is we're highlighting the camera, the science behind OGI, very basics of what we're doing. We're highlighting the camera's capability, and we're matching that camera's spectral, the spectral response to the camera. When we filter the camera, the filter that we chose in 2005 with the very first gas find IR. Well, actually, the very first one was a little bit different, but within a month we changed it to 3.2 to 3.4 microns, which is the common spectral response of all hydrocarbons. There are some that have a little bit more spectral response beyond, some earlier, but the most common to get pretty much all hydrocarbons. We don't know of any that don't fall into that. And as Yoshing mentioned, there is a response factor of over 400 that have been evaluated as far as how sensitive they are. In that 3.2 to 3.4. So we're engineering the camera and we're matching that with a spectral response of the gas, the molecular bonds of the gas. If you'll notice right here, all of these gases from 3.2 to 3.4, they all have at some point in time a peak spectral curve there. So not to get too dorky on what all's happening here, but that's realistically the basics and the simplicity of what an OGI camera is. Filtering in what we're able to do. And even though I have, made an analogy before, just imagine if you put on glasses and it just you could still see everything in black and white, but everything blue in this room just pops out at me, right? From the blue on the paper that Yoshing's reading to just the stripes of your shirt. Everything else is going to be grayscale, but the blue stripes just extremely pop out to me. It'd be very, and to do that, all I'm doing is I'm filtering the wavelength that I'm seeing in visual light to highlight and accentuate blues. And so very similar to what we're doing. That's kind of how we're utilizing the OGI. How do we tune that? The little green filter, and this is what is unique about FLIR compared to some of the other people that are in the technology, is we actually filter the camera inside the cold filter. What we are inside the camera body, it's called a cold shield. So our filter is actually attached to the detector of the camera. It's not externally. That does a couple of things. One, it does provide a little bit more sensitivity for the camera to be able to detect gas, right? So we're more tuned because the actual filter is built into the cold. Now, when I say cold, you'll notice the temperature that is cryogenic. You're down to negative 321 degrees Fahrenheit. That's how cold. And anybody who's used a FLIR camera, I call it the sound of money, and people don't like it. But I just, that when you turn that camera on and hear that hum, I love it. But other people don't. But when you turn that on, that first 7 to 8 minutes, what's happening is the camera has a little Stirling cooler that's cooling the entire camera detector down to those really low temperatures. And then so what we do is we put the filter directly on there. That's where, as energy comes in, it comes through the lens. There are some cameras and even some other FLIR cameras that have a filter built up in this area, but our filter is built on there. That does a couple of things. One, sensitivity. The other thing it does is you don't ever have to know if it's on. If a FLIR camera turns on, it will see gas. Period. End of story. And that is within our manual. So if you're doing AWP, if you're doing Quad OA, all you have to do to qualify whether or not the FLIR camera works from the manufacturer is turn it on. If it sees an image, it will see gas. It's impossible for the camera not to see gas if the camera makes an image. Whereas other ones, maybe somebody borrowed it and switched from one filter to the next, and then you grab the camera and you didn't know, and you're out there for a week using the camera, but you have a filter that only sees CO, and you're looking for hydrocarbons. I didn't find a leak all day, but you know, there are other advantages in having that cold filter. So as we filter it, you know, this is that little bitty energy that gets onto the detector and allows us to do that. As I mentioned, working principle, this is more of a, you know, guess. As the camera from the background, this is that thing, that energy goes, and this blocks the energy from reaching the camera. Again, that's going to show up as black smoke in that case, right? So in the case of using the QL3, you just tell it, what color smoke do you see? What color smoke are you looking at? And that's how you define an absorptive versus an emissive plume. So you do that. There are scenarios, as I mentioned, when you have a sky as a background, something extremely cold. You know, I used to ask the question, I just gave it away, is what's the coldest thing that we can do? Walk outside, put in anywhere we want. What's the coldest thing we can see? Some people say the chiller or the air conditioner. No, the sky. The sky is absolute zero. By definition, it's insulated by atmosphere and clouds. But the reality out the sky is the coldest thing you're going to see. So what happens when you're using the sky background? It's a little bit different. When you have the sky as a background, it accentuates. When you have the gas, it is actually a plume, a white smoke plume, and it accentuates the ability to be able to see that instead of blocking it out. And it makes it, you know, adds energy to the camera in that case. As we mentioned, there's two different types of plume, you have, and your emissive. This is the absorptive plume, also known more commonly as a black plume. How can I see that? You'll notice all of these images. You're going to have the ground as the background. You're going to have the top of the tank where the thief hatch is. You're going to have something in the background that is hotter than the ambient air temperature or the gas itself. Now, Boyle's law says that once the gas hits atmosphere, it's going to take the shape of whatever atmosphere or whatever condition it enters into thermally. And so when the gas goes out, it can be in a cold pipe system, but when the gas comes out, it's going to be ambient air temperature very, very quickly. So we can do that. And again, the ambient background, the background temperature, the ground, the tank, any of that is going to be higher than the plume temperature, the ambient air temperature. You'll notice when you see a white plume, you're either have an extremely cold something in the background. You know, we've seen, you know, scenarios where you do have a colder background than the ambient. You know, some cases, you know, if there's snow on the ground still, and it's still a little bit warmer than the snow. Sometimes on the day after a huge snowstorm, you may have something. You know, it may have a white plume or a lower temperature and an emissive plume. So when we say emissive, it's the gas is now emitting energy to the camera. The other one, it's absorbing the energy. When it absorbs it, it's not allowing the energy to go from the background to the camera detector, right? So from the background, from the plant, from whatever it is, that gas is absorbing that energy and kind of taking it up and saying, all right, I'm going to take the energy away from getting into the camera. That's why you can see. When it's extremely cold background, you would actually have it emit that energy. So the background is too cold. The camera doesn't get a whole lot of energy coming in. So the actual gas is emitting that energy to the background. I'll run through this next one, I think, and then maybe we'll take a break, but get into you know, the introduction more into QOGI. A lot of that was just kind of the OGI side. But this is more directly towards QOGI side. You know, in infrared, in OGI, the biggest statement over the years was qualitative versus quantitative, right? OGI was always qualitative. You know, since I grabbed my first gas finder as a wee little lad back in 2005, the number one question was how much gas is it? Since day one, right? And the answer was always, we don't measure gas. We just give you we do the hard part. We let you find it. And so now we can actually measure the gas. We can actually quantify an emission, which is change my humor to some degree. But and we look at stuff. Just curious, who's the leak on the left? It's the leak on the right. Anybody leak on the left? Okay. I think the leak on the right is higher. Who's still asleep?
Can we say the same?
Who thinks it's the same? Yep. So the answer is, yeah, they are the exact same. And those of you that have used an infrared camera, an optical gas image, or an infrared camera, you can change the level in the span manually. And all you're doing is changing the 256-bit grayscale of colors, and I can move it up and down. It's kind of like for years when we did just general everyday infrared in our world, right? And that's what FLIR does as a living as well. For years, when we did everyday infrared, I can take any infrared, I can walk in anybody's house here and I can scare the ever-living you know what out of you just looking at your fuse panel, because I can make it look like something's about to blow up, kind of like the right? It looks like that leak is just horrible compared to the leak on the left. But I can actually go into your fuse panel because you're going to have something, whether it's a microwave that just ran, or whether you're drying, you have your dryer running recently or running right now. Something's going to be pulling more load in your fuse panel. So I can change that manual level and span, make an infrared image look crazy and look like something's going to catch fire tomorrow. Same thing with OGI. You can actually change that to make it look different. And so, that's doesn't lie. I can change the way it looks, but the reality of happening, that's still leaking the exact same amount, no matter how it looked to the camera. Doesn't do anything but find actually happening within this with the right input to the camera or the quantification that is because a gas leak and that Yoshi and the Providence team have to face is everyone have the exact same leak pointing out of the exact same size hole over a minute. In the first 30 seconds and the second 30 seconds be a little bit different, just because the wind in this room, it is under the same conditions. Again, what we call the level and span camera is that range. It will affect the integration time. It will affect how the camera works. It's an 8-bit display. So you use an OGI camera from FLIR. You want to hit record. What it does, we actually compress the video so that all the video file sizes are not huge, so that you can actually save. So when you save and you get that MP4 file from FLIR OGI camera, it is a compressed file. What the quantification solution is doing is and that's why they save it in a special file, a FLIR file format called a .seq or a sequence file. Each individual frame is not compressed. Each individual frame, 30 frames a second, are uncompressed. Actually record each, and each one has its own, if you're 320 or 240, 76,800 thermals and intensity pixels. Each pixel has its own data point. And so they're analyzing each individual frame all the way down to the intensity of each individual pixel each time. And that's what they're doing with a 14-bit data with the quantification solution. And without additional measurement devices, difficult to even quantify access the leak rate. So really easy to use. But one of the foundations for OGI, but for QOGI is what is defined as the OGI triangle, QOGI triangle. What we mean by this is everybody's heard of the fire triangle, right? You got to have three things. What's in the fire triangle? Anybody? Anybody know what's in a fire triangle? Huh? Oxygen, right? So if you don't have those three, if you break one of those 3 points of a fire triangle, don't fire. You might get a spark, but you're not going to get a fire. So this is the OG. You have to have these 3 to be effectively do this. Some of them are pretty basic. G, you have to have gas present. If there's no gas, it's not going to look like you see gas in the image. Pretty simple, right? And so if there isn't a gas of some sort, and a gas has to be level of intensity, gas that the minimum spec of the camera. In other words, a minimum sensitivity, minimum leak rate, minimum sensitivity standards, whatever you want to find, noise equivalent, concentration length, different numbers that are out there from people. But that gas you have to have enough gas that meets the minimum sensitivity of the camera. That is present has to have a coefficient, or has to absorb energy in the length that the cameras develop. So, the other question I've had for 15 years is, oh, the camera sees gas. Will it see all gases? And I get the question quite often. Can you really camera? Can it? You know what would happen if we made a camera that sees nitrogen? Black screen all the time. So breathing right nitrogen. So as we've talked about, that's filtered in that absorption peak. You have a camera that's filtered for CO2, it's not going to see hydrocarbons. And the last one, there has to be a delta T. There has to be a minimum change in temperature. And what we mean by delta T, that is that background temperature minus the gas temperature. And again, as we talked about, the gas is going to take the shape thermally of the ambient air temperature around it. So the delta T is that background temperature minus that ambient air temperature. If you have those, to not only see gas, but also be on the same everything and the same gas. Right? There needs to be a guff bracket. Both of these standards. Just because that are out there that we can look at it just by the gas. Would be a true quantification. They're in the same. This is just a standard that when we get camera out, or the QL solution out. These are different factors that are built into these, and these are just the common streams of hydrocarbon. Hydrocarbon has different response factors. And if you look over here, we're doing which of these. Once again, they're the same. Response factor, conventional gas, we measure all other gases on it. So response factor of 1 is where we develop the quantification technology, and where it's just simple to look at quantification, look at gases, because propane has a response factor in developing response factors of 1.000. Okay. Methane, as an example, is 0.297872297. Methane is about a little less than. So even though these are the exact size leaks, the intensity of the response factor of methane is going to be different than propane. It's going to look different, not only to our eyes, look different to our QL3 quantification solution. And that's where that, again, that formula that our friend Providence put together, take this coefficient, and I don't know if you remember, if you back to the third slide, and all three built in. It takes into that and it says, okay, you tell me that then we'll be able to give now if you look close, that was 72 out, you know, but the wall was hot. I don't know what it is, but it's over 2. The ambient temperature, what's ambient temperature, right? You know, all of this, that's not the wall, but all of this is the ambient air temperature, this air around you. Beautiful day that all are open in houses and it's inside and out. You have that, it's not during the day floating on the trees and ground. So the air temperature out, all the way out here at the fence, temperature have to induce a small delta T. Now that delta T for the QOGI technology, we like it to be 2 degrees or more. And we'll talk a little bit if you go in, I think Yoshing will talk, remember, we talked a little bit about this, but if you go in a complete 0 delta, truly the exact same conditions, the exact same temperature in the background of the ambient air temperature, you can't see gaps. You have to have a minimum delta T. And for the QOGI technology, we actually put a in there called the delta T. I forgot what it's called, the delta T screening mode, where we'll highlight in red if you don't have the T top box, establish it at 72 degrees up and 2 degrees down. One thing, you know, we learned doing OGI demos in a room like this, it's very challenging to do an OGI demo, especially with QOGI, because I can go take a lighter or a cigarette lighter and hit the button, and I can hear it. But a lot of times the background in an environment, you know what you're doing. You want to try to get the AC vent in the background, a hot window in the background, to be able to do that, because that I'm just doing an image and you know, I just have the drape in the back. Well, it's just pass. I'll leave it up to the group. We've got another section here. They'll take a little bit of time. Would y'all want to take a quick break and come back, or grab a cup of coffee? And let's say 10 is 10 after, okay? All right, thank you.
by yourself?
No Johnny this weekend? Oh, really? Oh, because. These are my offices. Oh, no. And so where is that at? And then.
I guess that's good. Let's get out there, right?
Yeah.
All right.
And then also, is that the same thing that, well, that's a little further around. That's for friends on the line, that's really good, so we'll get it out. And you use the same.
Use a lot of.
Yeah, because they have that, they have some cars brought up, or to drive the route somewhere else, and that they did a bunch. But I don't think it's the same thing.
Yeah. So there's a.
Right back.
Yeah, we built those.
All right.
Yeah. Okay. And what's the difference in that?
That one.
Fix it up.
So that's, I think probably not.
Right, right now. Oh, yeah. Okay.
But then we're
Good.
waiting to see, so.
Okay.
Right.
Okay.
So, what region are you guys in? They're in California.
Oh,
So, here are Northwest of here. Okay, yeah, so we have, 4 miners. Okay. Oh, so, yeah. I don't know if you heard that or something, so to answer your question here about if emissions. Frequencies, as a regulator, we don't accept some in our agencies. Right.
And you're,
Northwest areas, yes. So just a regional agency. So it'd be similar, like, you guys are in Southern California? Yeah. So, yeah, so it'd be like working on that.
so we gave, during the consent, or during the first code, they did accept for about a third of our stuff.
Did they? The Southwest or San?
Well, we made a deal with them. No, it was South.
Okay.
And EPA, we had to get both to sign up on it. So on our non-bad actors, they approved about it. So we probably had 300,000 worth of, about 100,000. And they.
Clear with qualitative or just clear professional?
Regular.
Okay.
And they wrote it off. So we're happy to.
Interesting. And how did it go for you guys?
Well, we'd rather have that year round, but.
Oh, okay, so
So
you
you
actually
say how to, well, because it's not quantitative, right?
well, did you see more of an uptick versus finding leaks versus method 21?
Because those were ones that didn't leak. That's how.
And you're knowing back that.
And we're not never gonna find more like that, you know. Unless it's a timing. And so the components we know leak, they didn't allow us to reach components, they only allowed us.
Okay, so you guys are an actual gas company.
I was done with Chevron.
Oh, with Chevron. And so was it an internal operator that would, or would you send out like a
So
consultant?
we had our, so the way we did it is, so this is why we had to do it. So we had probably 30 guys that were contracted.
Yeah.
But they limited the amount of people that could go on site to go.
Yeah.
So what we did is 2 of our guys and 2 of their guys got third cameras. And they took third camera part, and the rest of the guys.
Okay.
So that got their force down to.
Interesting.
And then they said, okay, and then they said, they'll work 1 quarter, then the second quarter was okay. They said, like, go back. And we had a consent creation once that they allowed us to do.
You know, we heavily follow anything California does,
Right.
interstate, so it's, you guys are accepting it or leading that way, and I'm sure that we'll follow suit.
I don't know, because
It's a temporary step.
so EPA signed off on it too. But
These are different regions for EPA, so.
yeah, and they had to work. Yeah, and so that, I don't know if they'll even like that, but hopefully. I mean, I don't know.
I'm interested, I'm learning about it right now, and this is kind of like a
Because
first introduction to it.
But if you do a couple thousand a day, I don't know.
The mountain data and also speciation. I don't know if there's a broad, you know, because we're just looking at the SE, right? We're not looking at certain things like with your SIP and your, everything that's there. So that's going to be like a limiting factor. Like you put in, oh, or the species, that's what, how do you know that's there?
So that part, we have 13.
Yeah, I heard you say that. So that works. Yeah.
So I don't know.
We have not allowed drones at all for anything. We would love it for surveillance purposes. Yeah. That's crazy. So do you have a Southwest contact I could talk to that uses the drone?
I would, yes,
That'd be interesting. Yeah, I do.
Oh, okay.
and then the other part is, as you, like for flares and that kind of stuff.
Yeah, that's and something we, do you have any problem with ship loading and venting?
Yeah, so our worst areas anytime our ships float under, so our ships, like they hook up underwater, we hook it up and
Or are you within a mile of so
yeah. And I think we're the only guys in South Dakota. No, we didn't have a problem with that. But when we load the train or trucks, those are places that always consider rubberized stuff on there instead of there.
Oh, okay.
And so when it can be there, they go to separators.
Interesting.
So it's and part of it is like I'm eating people are opening, closing all that stuff all the time. So
Great job.
I hope Sorrow fix that, but separator are always best. Anything that
Your loading racks are bad.
loading racks are bad because
What kind of system do you have?
well, they have a rubber, part of the pad is the rubberized part that attaches to the rubber to the train.
Yeah.
That's in any station. I mean, you put a brand new one on it.
It's
Yeah.
Interesting. Did you do like a vapor capture, like distillation system, or do you flare off or?
Yeah.
California's different.
And then even our compressor, so our compressor is, yeah, hard to go, but whatever, you know, I got our, it's.
You guys got a two customer.
Either, so what you have to do, so they make us put pressure relief valve in our elevator. It's, you know, fantastic. They make it to run it, walk in.
Seems like they do have another one.
And so the.
Yeah.
Of course, they do studies.
The compressor, no, so they just literally, didn't know what to do with it, and it was at the tail end of it. And after they get all the reclaimables that they could get, they just didn't layer off. They just had a hose when you have to like a little gravel pit, and they just let it leak out, and that's what the operator had done.
Makes it easy for me to not miss it.
And it was just discovered.
Yeah.
During inspection testing. Yeah, so we're dealing with that, but that's not what we want to refinery, that's what the propane.
Okay. We had our compressor.
I'm trying to get this, Yoshi, where you can see it.
Yeah. So sometimes it's ever only.
It's hard to,
Only used in low.
so I don't have to look back this way. I was trying to,
Yeah.
so that's a lot better than it was.
Especially for that one. Top 10.
Decent turnout.
Hmm?
Decent
Yeah.
turnout. 20 people.
That's the best.
There when they use test stations and kind of thing.
Go ahead and start. All right, guys, I think we'll try to go ahead and essence of time, try to get some stuff started. Before I pass it over to Yoshing for some of the technical sides of this stuff, are there any questions about, if you've had a time to ponder all the great knowledge that I threw out to you? Any questions about anything so far? Yeah.
You said 2 degrees temperature difference for,
Yep.
Was that in Celsius or Fahrenheit?
2 degrees Celsius, yeah, so 3.6 F. Yeah, it's just easier to do see. But yeah, good question. Yeah, 2 degrees Celsius.
I'll make sure I'm understanding, right, is that it's the quantification you're
Correct. Now, again, you can put that in. So what you're doing is you're just defining as far as the accuracy goes, you're defining what the predominant gas within that stream is. So if I say, let's just say I have a QOGI gas and I walk in and I say 50% methane, 50% propane. It's not only going to say, all right, there's only 50% methane, and I tell the device that it's methane. It's not going to say it's only 50% methane, and that's the only thing I'm doing. It doesn't know how to separate the gases. It's assuming that in that entire gas, what can be viewed, keep in mind if it's half methane and half CO2 in a thing, it's not going to see any CO2, so it will be an accurate methane only. But if it's methane and propane, if there's multiple hydrocarbon gases, you're telling the quantification tablet what gas to set that response factor at. So realistically, you would be having a percent error of a QOGI gas, and if I tell it it's methane, the real quantification would be off because 50% of it is off by 3x, because methane is a third of the response factor of propane. It's still taking that and it's pulling that second half, the propane half, but it's only quantifying it at a third intensity or response factor.
So if you capture this image, bring it back to the office, keep data out, and change the response factor.
Yes, so there is the Providence team, and I don't know if I have this today. I didn't bring it on the 4C, but we actually have a spreadsheet that you can go in and say, all right, you ran a quantification and you have a leak of, let's just say 10 grams per hour. Okay. And you said it was methane, but in the reality, if you know it's 100% propane, you just go into the tablet and go methane, propane, run. Now you have the accurate reading. But if you know let's just say it's an average upstream gas in the US, right? So it's going to be 70% methane. Probably it's going to have a 2/3 ethane to propane ratio. So you're going to say, let's say 70% methane, 20% propane or ethane, and 10% propane is what you're doing. Because the other gases we can't see. We can't see H2S. We can't see CO2. We can't see some of the other gases that are going to be in a common stream. There are some that we can see like at 1%, like a benzene, but it's such a small number in that overall. So if I wanted to go and I could actually pull in my response factor calculator or I forgot the gas sensitivity, you pull it up and you say, all right, the leak was 10 grams per hour of what I did, and I said it was methane. But I had 70% methane, 20% ethane, and 10% propane, and it'll just immediately give you the exact number of that. But I will admit there is a little bit of extra work to that, but we do have the capabilities and a tool to be able to allow you to do that. That answer it? Yeah. Okay. Awesome. Well, I appreciate it. Well, I'm going to introduce Yoxing Zheng, who is the CEO of Providence Photonics. And again, we worked with them and now are in a formal partnership with them. So he's going to get over, talk a little bit about some of the theoretical stuff, a little bit deeper than I've talked to date. And then we'll get me back in here because I'm really good at dumbing it. I'll just dumb it down because that's just who I am. And we'll talk a little bit about the actual operation of the tablet itself, and then even do some test drives on the tablet, show you some call outs on how it works, and do that. So Yoxing, appreciate it.
Thank you, Craig. Yes, I think what he's trying to say is need me to do a little bit of nerd talking. So Craig mentioned about 3 factors or OGI triangle, and then this slide just to show how those factors actually affected the image, and consequentially, it will affect the quantification result. So the first one is that delta T. And one thing I want to emphasize also is earlier, a gentleman there asked a question about what's a degree, 2 degrees is Celsius or Fahrenheit. Another key factor is a lot of people get a little bit nervous when you say you need the 2 degree of separation and then say, I'm not sure I have that condition, but the background temperature is the apparent temperature, which means if your temperature today is 30 degree outside, the object, your background actually can be 35 degree. Even physically, if you put the thermometer on that surface, it's 30 degree, but apparent temperature could be higher because it also includes a reflective element of energy, which is actually helping the OGI camera, because OGI camera does not recognize if the photon, IR photon coming from the object itself or it's getting reflected. Doesn't matter. It all matters is whatever the photon comes from background is going to create that separation or create a contrast. So just want to add that. So the delta T, the higher delta T is going to give you the higher contrast. And then the absorption coefficient is going to have that. And then its amount, which is what actually the QOGI is trying to determine. So here's that fundamental kind of equation we use. The first 2 terms are the energy emitted from anything. Anything that is greater than, has a temperature higher than absolute 0, which is 0 Kelvin. Every object radiates some thermal energy out of that. And the radiation is a function of the wavelength and temperature. And the subscript, the TB is the background temperature, TG is the gas temperature. So if the gas temperature and the background temperature are the same, it will give you, basically this term goes to 0. 0 multiplied by everything is 0, so you're not going to see the difference, and the camera is not going to register anything. But the physical meaning of that is that gas molecule is going to absorb the photon come from background. But if the delta T is the same, it's going to emit the same amount of photon come out of there. So effectively, it's almost a no contrast. What comes in through the gas plume is getting out in the same amount. So you don't create that contrast. There's no black plume or no white plume. It just cancels out. That's why you cannot quantify that if the delta T is too small. And the next term is the things relate to the gas. First of all, as Craig said, that you have to have a spectral feature that is consistent with the filter in the camera. If it's not, then you're not going to be able to see that. And that's, for example, that's the reason you cannot see nitrogen. Nitrogen does not have any spectral feature in this camera, in the window in this camera. So there's nothing. If this alpha, which is a function of wavelength, if that is 0, it will make this term as 1. 1 minus 1 is 0, then 0 again. One is if you don't have any gas, then that also have the same effect as your coefficient is 0. So all those three conditions is going to, presence of all those three conditions is going to cause a difference in the radiance each pixel record or capture. And we use that data to do the quantification. So here's a chart. The x-axis is delta T. This chart is actually just calculated based on the equation in the previous slide for the same gas. So if you have a delta T is the x-axis is delta T, and the y-axis is that intensity difference. And we have a different amount of gas in that term, in that three kind of element there. So you can actually develop a cluster of curves that changes with delta T. So for the same 100, let's just use a higher one, 8,000 ppm meter, this top line, 8,000 ppm meter, fixed, everything equal, just because the temperature change, you're going to have a different delta T, as suggested by that equation. So you're going to have this equation, this cluster of those. So if you change it to different concentration level, you're going to generate a different intensity difference. Okay. So, but if you actually fix delta T, you have this kind of vertical line that intersect each of those concentration line or ppm meter line. So you can extract that data and then you plot that on this right plot. Then you can see the very nice linear relationship between what is the ppm meter and the intensity difference you're going to see in the camera. So that's really the foundation of this quantification. There's a very good theoretical foundation. Given the certain conditions, the only thing that drives the intensity difference is going to be how much gas is in there. ppm meter means the column density, which is how much gas is in there. So in order to make it work, you have to recognize which pixel is the gas plume, which pixel is not. So the process we call the plume extraction, we have to recognize, we have to basically extract the pixel that represent gas. That will be stand out from the background. And then we can derive the concentration path length at the pixel level, which is that delta I. And then we aggregate all that across the boundary. And then it basically that derives a parameter or signal. In that case, there are two things that drive the quantification. One is each pixel, if that has a higher ppm meter, is going to give you, each pixel is contributing more because each pixel represents a larger amount of gas represented by that pixel. Second is see how many pixels crossing that boundary and what the rate. So combined with those two, you can do a quantification. That's how the kind of in principle, this is how that works. So this one, just another way to show this, but we are actually focusing on the ppm and the pixel level. A new feature of this QL 320 is you can draw a box, say, I want to know what's the highest ppm reading in this, which is very similar to what you are actually reading with the TVA, because that's really a draw sample from a point in the gas cloud around there, and then get the ppm reading, except it's a ppm, and here is a ppm meter because it's count for the depth of that. So you can the new feature in the current version of QL 320, you can see those reading is going to give you the maximum ppm meter reading out of that. So that's the principle to quantify the ppm meter, which is actually less complicated than the flow rate type of quantification. Then what we do is we're going to, the algorithm is going to compensate for delta T and some other conditions, because in order to quantify, if a pixel shows a larger contrast or larger difference, I want to make sure that difference is not, basically, I want to separate if that difference is caused by delta T or is caused by the amount of gas in there. So I can standardize everything into the same delta T, and then what's actually left is the contribution by the concentration. So I can uniquely relate that to the concentration. This is how that works. So we can establish this, then we can do, once we accomplish the canceling out other effect, basically, or equalize every other effect, then we can do a calibration. And we can, just like any analytical instrument, even the sniffer, you're going to use the methane or propane to do the calibration. It's the same thing. It will show the signal to the actual ppm meter reading. This, in this case, if this is a mass flow rate, then you know the flow rate, and then you know the signal. Then the two things is going to give you a nice calibration curve that help. Once that is established, now you can apply that to your actual detection. You have a question there? Yes. Yeah. It's for a given gas, that the spectrum feature is fixed. Yes, if you have a different gas, that's why we have a response factor, which is the same as a sniffer. But technically speaking, you use a propane to calibrate. Actually, if you go to the EPS leak detection protocol, one of the appendix actually lists the response between the methane versus the other compound. In most cases, nobody cares about that. But theoretically, it is whatever you are reading actually can be affected by what nature of the gas. So that's the same. And during the break, or earlier, I don't remember break earlier, there was a question about the mixture. FLIR can provide you with a tool that when you get, if you know it's a mixture and it's significant enough, you can use this result using that tool to actually break down what will be the mass emission rate of each species that make up that mixture. the camera really cannot differentiate each chemicals or gases. It's just measure the aggregate, the radiance difference. You have to use this extra tool outside of this quantification to break that down based on their response factor, based on the knowledge. You have to have knowledge about what's the composition of that gas mixture if you have.
I think maybe the question is, you're saying it's a meter, ppm meter, how does that, how is it getting the meter when you're two-dimensional?
Yes, yes. Okay. Okay. Yeah, you are technically you are not really measuring the concentration. It's a concentration product of concentration of path lengths. But if you can roughly estimate, if you know that in this case, for example, in this case here, if you know the physical dimension of this pipe that leaks that, if that is 2 inches, for example, so then you can read the ppm meter here in this case we're talking about the ppm meter, not talking about the mass rate. So if that is 10,000 ppm meter, and then if it's a equivalent of, if you visually see the depth of that plume, assuming that's a cylindrical, which means the depth of the horizontal, I mean the cross screen, you can see it's the same as the third dimension there. You can divide by that dimension, then you can estimate your ppm meter.
So what you're saying is, if it's, we're assuming our ppm meter is an assumed 1 meter depth.
Yes.
And so if you know that depth and say that it is 10 centimeters,
yeah,
right?
Then you divide
Then,
by 10,
yeah,
that raise your ppm meter, ppm value higher by 10 times.
If that answers your question. So yeah, we could put a parameter in there and says if you wanted to use parts per million meter and you know the exact depth of that leak, and that's easy when it comes out of a hose or out of a pipe.
Yeah.
But when it's coming out of a flange, it's a lot more challenging to understand the depth of that. But if you do know the exact depth of the maximum intensity area of that leak, which would be the exit velocity point of a open pipe, as an example, a vent, if you will, you could actually find the exact concentration. If it's 2,500 parts per million meters, and you know that it's 10 centimeters in depth as far as the diameter of the pipe, then you know it's a 25,000 ppm. It's a true concentration number.
Yeah. So the effect of the camera see is the same between those 2 streams. One is a 1,000 ppm, but is a 1 meter the width of the plume. Another is a 10 centimeter of the plume, but it's 10 times a higher concentration. And then the result of the ppm will be the same. So you can establish calibration, and the calibration curve looks like this. So here's a signal, which is aggregated from all those things we just talked about. And then here's the leak rate. And it has the very nice linearity. Then when you actually now apply that, whatever the signal the algorithm generate, you can relate, basically you can find the leak rate. That's how this works. So now have a little bit of discussion about the detection limit, which is not exactly just for the QOGI. It is applicable to OGI in general. So in other words, how small of a leak the OGI camera can see, which is again affected by those factors. One is delta T, another is what kind of species. The third one is what we are trying to determine as a minimum detectable amount. So the factor that impacted the detection limit is delta T, which is apparent temperature background minus the temperature of a gas. Second is the camera design, which means that filter is that what is the filter? And I know FLIR customized certain things for specialized for benzene. So your benzene camera versus a general hydrocarbon camera is going to have a different filter. Then the sensitivity between the two for a same compound is going to be different. So that's a factor. But once you have purchased the camera, that factor becomes fixed. So it's no longer a variable. The only variable is delta T and the type of gas. And then there is other factor that is not explicitly expressed in the equation, which is a distance and wind. Why the distance matters? Because if the leak is very small, it's small enough, and at a certain distance, it does not even fill a pixel. So your 1 pixel is going to have a radiance half from this gas plume and half from background. Then you're not really getting the representative detection limit. So that's why the further you walk back, the lower the detection limit is going to. It's going to limit your ability to be able to detect that. And then the wind help the dispersion. So if the leak comes out very quickly dispersed, then you reduce that ppm meter number, and then that affected. So it's indirectly affecting that. And understanding all those things really help to understand the limitation of the OGI camera and the quantification. And we have the detection limit can be expressed in be characterized in two ways. One is the ppm meter, which is really at the pixel level. Just say how much of the concentration you need in order to generate the signal to be able to recognize in the camera. Another is the detection limit as a mass emission rate. And so we've done a lot of work, both from the theory aspect and also the actual practical sense. And we developed this equation. The ppm meter detection limit, DL detection limit expressed at ppm meter, is a function of delta T with the two constants, alpha and beta. Again, this is assuming you are dealing with the same camera, in this case, the GF320. And if you are dealing with the same gas, if it's a different gas, this alpha and beta is going to be different, but it's still a constant. We have much more detailed discussion in a publication. Here in this, you can follow this link, actually get a full explanation how this detection limit is derived. But the key thing you take away from here is a detection limit expressed as a ppm meter is some sort of function of delta T. The higher the delta T, the easier you can detect. The higher the delta T, the lower the detection limit. The lower detection limit means you can detect a very small concentration. And here's a graph showing those kind of give you a visual of how those impact the detection limit. The x-axis is delta T. As you can see, delta T is very important for the detection limit. And then the y-axis is the ppm meter, how much you can detect. And then the orange line is for methane, and the blue line is for propane. So as you can see, the orange line is much higher than the blue line, which means the detection limit of methane is higher, meaning that you have to have more methane under everything equal between those two gases. You have to have more methane to make it visible in the camera than propane. Okay, so, and also, as you can see, when it approaches zero, this actually goes towards infinity, which means that no matter how much gas you put there, it's not going to be visible, if theoretically. But in practice, there's always some sort of temperature difference, just because of the physics that whatever is in the ambient is not going to be the same as the background. But as the delta T go beyond the either negative or positive 5 degree, the curve becomes pretty flat, which means delta T is not as big of a factor. So yeah, that's, and we kind of, it is a little bit of arbitrary when we said to say, in order to quantify, we really want to have delta T of 2 degree. That is, when I say somewhat subjective, is why not 1.9? Well, you can. So we just pick an easy number to remember. 2 degree is what I think it would be, it makes sense. That's. And another interesting thing is this, well, the delta T is going to, or whatever detection limit is going to cause this visible in the camera. You can see it or you cannot see it. But the fact you can see or you cannot see is the grayscale in the camera display, which for this GF320, it's a radiometrically calibrated, which means whatever that grayscale is corresponding to a temperature. So it's an apparent temperature measurement. So what we are saying here, our detection limit is developed based on assumption that you have to have 1% of contrast. What that means in the 8 bits display, which is 256 different grayscale, you have to have a couple of grayscale differences for your eye to recognize that difference. If there's only one grayscale, it would be very, very difficult to see that. So, but that grayscale can be, because it's a thermally calibrated camera, you can actually translate that grayscale into a temperature difference. In this case, it's a mini Kelvin. So as you can see, that the 1% contrast actually is pretty constant. And there's some reason for us to explore that, because we can tie this parameter detection limit into a traditional camera specification, which is a thermal sensitivity or a specific parameter called NETD, right? The noise equivalent to temperature difference. So then you can use that parameter to assess your camera's ability or sensitivity for this. And here's an interesting thing. So we take this image from there, and then there's a tank there. The background is pretty smooth, and then we have a tank, but we also have some gases there, and to show that this is a purely background. This is a gas tank plus gas, and here's the grass. So we actually, in order to recognize the plume, you have to see the pixel, the dark kind of pixel that can stand out from background. And so there are two kind of dimensions that affect that. One is a spatial. So you have to be able to, in order to recognize that as a plume, the difference that caused by the gas need to be greater than the noise level around it. A noise level either temporally, which means from frame to frame differences, or spatially. So it's just for the same frame, it across this, like in this grass area. If you have a small difference here, it's not going to, it's going to obscure your gas signal. So here in the very ideal case, this background is very clean. The standard deviation is very small, which means if you have a gas there, it will stand out, allow you to see that. And if this second one is gas, see, now you can see once you add the gas, this is a tank background. Once you add the gas, it shows the numbers stand up. So you can actually, it's separated from the background, you can see that. And here's in the grass area, so which means even without the gas, it's already at this level, you're not going to be able to detect the same thing. So that's why in the early days, the TCEQ did some study and then figure out, oh, the detection limit is a function of what is in the background. This is why. Because if the background have a lot of texture, not very smooth, you're going to have a harder time to detect the very small leak. So those two red lines is the camera's NETD, and then you can see in order to be able to detect that, you should have a couple of factors higher of the variation than that to be able to detect. So overall, the key factors here is there's distance, there's minimum kind of leak rate, and delta T. Going back to one of that new kind of compared to that OGI triangle, the new thing when it comes to detection limit is the distance that is new here. So we developed this chart just to see if you have a certain delta T and a certain distance, this curve is below this on the below this curve, you have ability to detect this. In this case, if you set your target as 30 grams per hour leak rate, you can accomplish that if the condition is on the below this curve, which is you have to have a delta T. For example, if you have a 10-degree delta T, you can accomplish a detection limit of 30 grams per hour and the distance of 20 feet or closer. But if you go beyond 20 feet, you are not going to be able to see that. So this will be a helpful kind of a tool to draw some boundary about your ability to be able to see gas in OGI camera. I believe that's the last one. Any questions for this part?
Thank you, Yoshing.
Thanks.
Yeah, that's a good way of tying in the calculations and the formulas that the Providence team have been working on for realistically 10 plus years, and tying it into true application of utilizing the camera to establish detection limits, so that again, one of the challenges until 2016 there never was really a detection limit. In 2016, what is now turned into the global parameter detection limit for a gas leak was established in QOGI. It's a 60 gram per hour leak. And so you can actually input that those types of numbers. So it's how you can actually pull some of the background and foundational data into this. What I'm going to do now is I'm going to kind of move this in a little bit more into the actual use of a quantification tool. In use of the technology, and kind of go over what I'd like to do is kind of go over it in basic form in a presentation here, and then we'll move into actually showing you in real life examples of how the quantification solution would work, and even show you some call outs for challenges in utilizing this. As I mentioned earlier, there's two ways to use the solution. One of them is going to be what we define as tethered, right? So you're going to have a USB cable plugging into the device and directly into the back of the camera via USB. There are some advantages there. You get a little bit immediate feedback, and there also are some user parameters that you can use tethered. But one of the most common ways is utilizing our Q mode. And what you see right here, this is the red number there is we've implemented the delta T compensation or the delta T alarm into the Q mode feature. So while you're operating the camera, you're holding the camera for quantification and storing it in Q mode, you have the full capabilities of understanding the delta T just as you would using the QL320 tethered to a camera. So you can use this in a class 1 division 2 area, store however many different things, however many devices you'd want, but you would need to have the camera tripoded even if you're using the Q mode feature. A little bit about what we're getting into here. This is just the different features and some of the newer features and the actual QL320 tablet itself. As we look at the tablet, this is the walk around the tablet. I'm not going to get into each of these, but there are some features on here that we don't even utilize of the tablet that can be turned on. This is like number 7 is a camera launch, because there's cameras on the tablet. We've disabled that. Most people aren't using that. It does not apply to the QOGI technology. It can be enabled if you want to use the tablet for other aspects, but you simply turn it in. If you wanted to plug it in on the side here, you would plug it in via USB here, or you could actually either USB, or it does have a direct micro SD card. So the cameras from FLIR store on an SD card. So you could, if you had an SD card which has a micro SD card, some guys like it, some people and gals, but some people don't, because that little thing is pretty microscopic when you start taking the micro SD card out of there. But it's going to run on battery. It's going to have about a two or so hour battery in the QL320 tablet. Very easy to use operation, and it's just a computer. This is, we'll see in just a minute whenever I turn it on. It's just a full-on computer. We do have online, pretty easy, quickstart.ql320.com, a quick start guide that we also provide I believe we provide with the delivery of the tablet, but very basic in what you need to use. If you are connecting it via tethered mode, you would need to configure the actual camera itself a couple of different ways. In other words, you need to tell it what type of USB connection you're going to have, being able to use that. But when you do this, that's the step process. You hit reset, you hit capture, and now you're storing and you're quantifying a gas leak and utilizing this. But again, all of that's really easy. All of it's online. The user interface, or kind of what this is, when we did our formal partnership with Providence, we hired our FLIR UX team, user experience team, and talked to users and said, what do you want this to look like? What would make this easier? And this was the outcome of the QL320. Realistically, the meat and potatoes of it is all right there in the middle. But we wanted everything to be sectionalized in how you might operate this. The first one is the user data inputs. As we look at the user data inputs, there are a handful of things. Some of them are automatic, like the lens. The original QL320, you had to tell it what lens, which would be somewhat challenging. So people may not know. Now it's metadata in the camera or in the Q mode file, so it automatically knows which lens. So you don't even have to put that, but you have to put the polarity, the leak type. Again, 95% or more are going to be, if it's a larger, huge pipe, you would want diffused, or if it's something that's more like a seal. The majority of what you're going to see is going to be more of a point leak. Distance, temperature, the composition, the wind speed on average. There are some extra things with campaign and memo. You can actually type a note on each individual one to say, hey, this is what I'm doing, this is where I was, this is what I was looking at. And then campaign is just a fancy word for file folder. Where do you want to store? Where you want to store all the data. Another new feature since the inception of this is called masking. And what we mean by masking is you're able to take that circle. This is not applicable to the concentration use of the camera, but if you're doing this in mass or volume and you wanted to do masking, there are times where you may have an issue, as an example, if this were a very reflective pipe, sometimes that reflectivity just sees ambient air conditioner. If it was a very polished aluminum type of pipe, it would just see ambient air conditions because of its reflectivity. So now you could actually come into the unit and actually mask out or check out and notch out areas of the circle to tell the technology to disregard those. And we'll show you that when we get into the training of the unit and the training of the QL320. Get into that here in just a little bit. There's overlays. There are only 3 overlays, very basic. Most people keep those on all the time, but you do have the capability to turn those on and off. The first overlay is going to be delta T. You can barely see this little bitty red area just to the left of this vertical pipe. That's going to be the only really areas within this video or within this recording in which there is a delta T challenge. Now, if you have that on there, if it's inside the circle, the algorithm knows to ignore those pixels. But it's easier to see if you have the entire circle covered in red, then you're going to ignore every pixel inside there, or half of it, and if the gas is moving around there. And so you'd be able to do that. One unique thing about the Delta T, and as far as operation, being an infrared guy for 20 years, we always tell infrared people, non-OGI, just a straight infrared, is never assume that it's a fault. Because in infrared, we have what's called emissivity, and emissivity is the opposite of reflectivity. An object emits energy or it reflects energy. Okay, so if you have something polished aluminum, you can't use an infrared camera to measure it to temperature-wise, because it's always trying to measure the reflected temperature of what it is. So you might be looking at a fuse panel in a boiler room and you see, wow, this fuse is hot. It's just a weird looking hot though. It's just like a little sliver. I always tell infrared people, assume that what you're seeing is wrong and try to find this accurately. And with this, we even go a step above and give you the delta T compensation. So now you can actually look at that leak in a variety of different angles to be able to make it easier for you to either detect the leak in OGI or quantify it with QOGI. And these are the types of things that you'd learn in our certification course. The second one is the Plume Overlay. Most people like the good, pretty colorized plume. That would not be live on the Q mode within the camera at this time. So if you are utilizing the camera, you would not have the Plume Overlay. That would be the only masking or only overlay feature that would not be live on the camera. And then you have the boundary. You can turn the circle on or off. I almost always ask people, recommend keeping that circle boundary on so that you can see if there is a situation in which you may be getting some error, some grass, slight grass moving, or a cloud or something, or the edges of a tank top, which we'll talk about. Again, I've got some really good examples to show you in operation. The other one is the units, Celsius, Fahrenheit, feet, meters are the basic ones, but there's also the quantification. You can choose the mass, you can choose volume, or you can choose concentration in those units. There's 3 modes, and this is one of the newer features that we have in here. One of them, the original QOGI technology, and really the QOGI technology in fundamental is pretty in depth. There's a lot that you can do there. And working with Providence, we agreed that let's make a simplified mode. We're just go out there and hit a button and it gives you a number. Most quantification technologies give you just at the end of it, it's not changing. Keep in mind, if I look at a plume live, it's always changing. If you look at a gas leak, it's never just goes up right 90 degrees and shows a very consistent. It's turbulent, it's wind speed, it's exit velocity. There's all kinds of different factors that change the way any type. If you've seen an OGI video over the last 15 years, the gas plume, it's always moving in really unique patterns, even in a controlled environment in a lab. Realistically, you've seen some of the videos when we're showing you coefficients and we're showing you gas intensity and delta T. Those are in a lab, and every time the leak looks different. So we've added a normalized mode, which makes it very simple. You just say go, gives you a number, walk away. We do have an expert mode that allows you to record it over a minute. The more time that you record, obviously, the more data you collect, the more accurate that you'd get. That would be on the tethered mode. The load button allows you to pull in and load those Q mode files or previously recorded files. And then the demo mode is what we're going to do today, is working with the Providence team and said, we need to train people, we need to demo people, we need to be at conferences like the 4C and be able to talk to people and show them how the technology works live. And so we've got some real and true in-field demos. The great thing about the demo mode is if you use a unit and you have your own LDAR team and you have examples that you've used, whether it be a Q mode file or a live QL320 tethered instance or video, you can use those as your own demos, and you can add to the demo cache or the demo the demo options of different videos that you can use. The manual sensitivity, this would be only in the tethered mode. Now, once you record something, you can pull it in, but when you're tethered, this allows you to change the intensity. If those of you that may have used a FLIR camera and used our patented high sensitivity mode feature, right? So if you've ever used it, you've got from 0 to 7, you've got 8 different levels of high sensitivity mode. When you go to 7, it's like, oof, this is a bit much. There are customers that, if you really want to find that extremely small leak in the worst conditions, the smallest delta T, you can utilize that 7, but it almost starts seeing just too much stuff, in my opinion. Most people use it at around a 2 or a 3, myself included. But that's that high sensitivity mode. Well, we have that in the QL. You can change the intensity, and I'll show you some examples here in a minute. I mean, you go all the way up to 10, you might be having too much intensity as just atmospheric changes, within the background, it starts seeing actual air movement at some point in the unit. The bottom, this is going to be measure or record or rerun a previously measured one. And another new thing is we added a simplified results bar. Historically you hit save and it just kind of waited and hoped something happened. Now you can actually see this live bar saying, all right, you're 18%, you're 27%, you're 50%. Okay, got everything recorded, start moving on. Just makes it a little bit. And then the dialog box, this is really, really basic. And a lot of people said, well, what is this? What it is dialog box. But you can just see the previous recording, the previous run that you did. Maybe you ran it and then you're just like, oh, you realize that maybe I had the wrong composition, or I maybe needed to change the temperature or the distance. I had a distance set on a previous. I can look at this and say, I know that's not, 50 feet. This looks more like 10. So you can change that and rerun. But that way it'll give you the previous recording really right there in the dialog box. To give you actual live examples of some of this is the delta T compensation. As I mentioned, this is, this is the, if the circle was here and I turned off, you can see the boundary is turned off right now. I only have delta T turned on. What would happen if I'm recording the quantification, you would not see, it would ignore any of these pixels that are in the red area. There are times that you just can't, there are times that maybe something inside the boundary is going to be under that, it's going to be the same ambient air temperature, air conditions. And so you would have that, and it just ignores those. And so you can actually quantify. Then you have, this is the Plume Overlay with a delta T turned off. And this is just a single snapshot of what the Plume Overlay, and now that's just pulling the delta intensity, right? What Yoshing talked a little bit about. It's pulling out those pixels that have a change in intensity over time and highlighting those in a colorization plume. And then you've got your mask. Another new feature is the mask down here. As mentioned, there's a scenario right here where the reflection of this pipe is telling the technology that might even be a leak, because maybe there's something moving in the background. It's a really highly reflective pipe. So there are times where you can actually just, on the screen, you just mask that out, and using this to give you a much more accurate reading when you're utilizing this. And I'll show you some masking scenarios and capabilities. One other new feature is the ability to do multiple masks. In this case, maybe I want to mask out if these were, and these aren't really that bad, if these were highly reflective. You can see right here, there is a little bit of reflection that causes the technology so that you can actually mask out as many different sections as you want. You can go out there and add 10 of them. You start running into challenges looking on the screen and seeing what's happening. But what happens is now as this moves, it ignores anything that might go inside this open area. So it's just on the screen. You just on the QL320 unit itself, you just simply touch screen and you mask that. It makes it really simple and easy to use. And then you look at the auto and manual, you'll see I'm actually running this, the sensitivity level. You'll notice at 1 you couldn't see anything, but when I get all the way up to 10, it almost has too much energy. It's looking for too much. If it were a perfect condition with an extremely high delta T and a very small leak, maybe 10 would be more appropriate. This is one where you can obviously see it's not the ideal conditions because there is a minimal delta T here. There's not a whole lot happening, but as you get up there, I believe when you run the camera in Q mode or in just when you just run this in not in auto or in auto mode, I believe it's a 7 is the defined sensitivity level that they try to utilize. When you're using our Q mode feature, the one thing is what we're doing is we allow you to record that sequence. You just record on that SD card and transfer to the QL320 in some way. Again, you can take the SD card out and you just have to either USB or directly with micro. The unique thing is, you could actually have somebody sit in your office. You could pull the stuff out after the day's work, put it on an X drive within your organization, and somebody could analyze it somewhere else. So you don't actually have to have both of them connected or even talking to each other. You don't have to tell this QL320 that you can use that. But one thing that is important if you do the Q mode is that data parameter. It needs to be accurate. You can change it, right? You can change it when you're in Q mode, but a lot of times you may not know. You wouldn't know what was the ambient air condition or air. I keep saying air conditioning. Maybe it's because I'm warm, but the ambient air temperature, you wouldn't know what that is when you're sitting back at your office. I can input it into the QL, which you need to take good notes. So on the actual, each individual Q mode file, you can go in and change that input parameter. The ambient air temperature, if I'm at a well pad for an hour, that ambient air temperature is probably not going to change within that hour at a well pad. But if I'm at a compression station and I'm outside looking at some looking at some separators or looking at some components outside, and then I go inside a building or inside a more enclosed area, that ambient air temperature is going to change much more dramatically. And so you just need to make sure that those parameters are right whenever you try to save it after the fact. You saw the drop-down menu. I was showing you the user input data from the QL320 itself. Well, you notice this is a screenshot of our FLIR GF camera with Q mode. You'll have the exact same parameters. You can put in the ambient temperature, the distance that you are from the camera to the actual leak itself, the gas type. I don't think this one, and then there is a parameter for you to go in and turn on the delta T, which is a new one. I don't think I have that on here. But yeah, all this data, it just goes directly on the SD card and saves it as a unique FLIR file called an SEQ file. And as you're looking at this, the one thing, the lens is automatically done. The black plume is probably the easiest one to fix when you're using it after the fact. I can look at it because that's been one of the, when I've gone and done some analysis and testing in the field, I get back and, oh, and this doesn't look right. I'll look and I say, yeah, I've got it set as a black plume and it's a white plume because it was up in the sky. And I was looking at a vent on top of a tank or something. But all this data is input both in the camera and can be adjusted. In the camera, we also have the delta T screening. So you go into the setup area right here, and then you just simply tell it, I want the delta T indicator on. It's set at 2. You can change that, but we pretty much recommend you lock it in at 2. And as Yoshing said, there's not a whole lot of foundational theory behind that. That was just the best number to use, and it's a good round number. If you change it to Fahrenheit, you can set it for what you want, but it would be set at 3.6 Fahrenheit. And then when you get to the actual tablet itself, when you get to the ability to do this, you just simply open the tablet, you open the program and hit load button. When you hit the load button, like I said, the tablet is nothing more than a PC. Those of you Apple guys, we're sorry, it doesn't look like an Apple device, an Apple computer. But just like a standardized PC, you would simply go to load, pull up your menus, and you find that SEQ file. When you find that, you open it. And then the second you open it, it would start running. At that point in time, you could change these. If you change any of the user data or the inputs, what the way that you want, or the units, the way that you want the output number to appear. If you change any of those, it would restart the process over. But it would run until the results is 100%. And after you're done, in this case, in this actual leak right here, you're looking at 12,000 standard cubic centimeters per minute is the leak size of this. And again, if I wanted to see a different unit, I could set it up and rerun it in a different unit, and utilize it like that, parts per million, standard cubic foot per hour, whatever it is you'd want to do. Really basic in use. And then the output of what you're going to have in the Q mode or the QL320 is going to be 4 files. Very, very basic. So what's going to have, you're going to have your sequence file, your special FLIR SEQ file. That's going to still be there, but then it's going to just simply create a folder. And in that folder, you're going to have 4 files. The first one, the first one, this is actually not SEQ. It's called a DAT file. And this is going to be the data file for all of your QL320 data. This is what it processes after you run it for the first time. It really does process it faster and easier when you run a data file. Outside of that, you're going to have your raw video. You're going to have a subset of the video. It's a few seconds long of the raw video of the leak. You're also going to have your Plume overlay only. It's not going to have the delta T. It's not going to have the ring boundary. It's going to have the actual Plume overlay. So you get a raw video with a colorized plume directly in that folder. And then you're going to have a very basic, and we've looked at different ways of doing this, 1-page report with an image, a single frame pulled out image, and the quantification results right here. All of this user data that you put in would be there for qualification, so somebody could look at that. But you'd have all of that with the results, very basic, simple, and easy to use. I'm going to try and see if we can switch screens. See how this works. Not that. A little limited in the technology that, oh, what I want to do in a new meeting, got it. A little limited in the technology here, getting this connected to a projector as well as connected to everybody else that's trying to join us. So I wanted to kind of show you the QL320. We'll start this and then we'll take another break here and maybe a little bit, but what this looks like, you know, those of you there, this is just the screen of the tablet. When you turn this on, the Providence team who does the manufacturing of these, they don't make the tablets, but they put the QL and get it all set up. This is all that it looks like. You're just very basically going to have the QL320 icon, and then you have a couple of QL320 documentation PDF files. The quick start guide that we talked about, that's available online as well. The download or the newest actual manual. And then we call it the release notes, because one thing in working with a company like Providence, they continually, consistently make this product better. Some of it is feedback from the FLIR team. Some of it is internal understanding whether it's a bug or a fix. Some of it is your feedback. When you all call us or Providence and say, hey, you know, this is great, but you know, if it's something that can be done easily without a dramatic revision, they do a very good job of implementing small fixes into this without having to have an entirely new firmware, an entirely new version of the QL320. So there is a release notes page. All 3 of these have direct link accesses. I think it's releasenotes.ql320.com, quickstart.ql320.com, and I believe manual.ql320.com. So very easy to access online to always get the most up to speed, but it's also directly on here. As I mentioned, this is nothing more than a standard computer. So I'm going to go, I have my documents tab here where I've got some recordings of different things. I've got live my training videos that I use and what I'll be using here today. Austin is some stuff that I have set aside for this this course. So for while I'm here this week, and so super easy to use. Again, if you can use a computer and everything, as you can see, I don't have a mouse or anything. All of this, everything I'm doing is completely touchscreen. So I can pull up a keyboard if I need to, or anything like that. Before I get into this, talked a little bit about it. Are there any questions? Like I said, I want to make time for questions if you have them before I kind of get into some of the operation for a little bit, and then we'll take a break after that. Yeah.
Close to each other.
No, you would need to film those separately. Yeah, and there would be, if two of them are going and one of them, say they're both moving in the same direction, there may be a little interference on the second one, but the reality is because that second leak starts outside the boundary and moves in, unless it moves in directly with the point release of the other one, it would ignore a fair amount of the second leak that would be going in there. But the reality is there is some concentration of, there is some leak that's moving into there and moving into that. But ideally, the way it's set up today, you would need to do two separate recordings of that.
I kind of, let's say, you ever get like a cloud instead of a balloon, you can't get outside the.
Like thief hatch? Yeah, and there are the limitation of distance can be a bit challenging to get a super good reading of that. You could change that from a point to a diffuse leak. Now, if it's a big enough leak and you're standing there and it's just blowing right into you, I'd probably recommend you get out of that area anyway for health and safety purposes. But if it's a super big leak and it's blowing around and it's just covering up everything, you could set it up as diffuse, but that would be a situation that would be a little bit challenging. Just so much going on with the technology in doing that. The way the technology is today, I will say that the other challenge a little bit is the tripod mount on top of a catwalk can be a little bit cumbersome.
So is the angle you film from give you a better reading than another angle?
Yeah. So that's more of an OGI than a QOGI question. The reality is not just seeing it; they're not just quantifying it, but it's also seeing it. I think I talked a little bit in one. I don't remember. I've built so many presentations for this week. I don't know which one's which. There are scenarios that you want to take into account when utilizing, QOGI technology. I think I talk about in the tips and tricks section of this, and what it is a leak coming directly at you or directly away is much more challenging to even see what's happening, much less quantify a leak going horizontal. And that's just common principles of OGI as much as it is QOGI. Yeah, no problem. Yes.
I understand the distance limitation, but do you have any examples of a flare that's like a smaller flare source with the QL320?
I don't know if we have files there. I know that they've utilized it. Yoshi, I don't know if y'all have very many examples in your field studies of doing a flare. I mean, the distance limitation and using this on a flare, and sometimes if this is a wide open unlit flare, that there are limitations in the top end about quantity that this can quantify. It's much higher than a high flow, or anything like that as far as the top end. But I don't personally have a QOGI or QL320 or Q mode file for flares. Have y'all done any experiments with that? Yeah, John may. Yeah.
General. Yes. In that case, about the calibration setup.
I know, I do know that, like I said, it's been a couple of weeks, but I've just been out in the field, just seen a completely unlit flare and they thought it was lit. That's a little easier, but yeah, the big white ball that you see at the top of the flare would make it challenging to use this in quantification of the flare as well. Yep.
If it's actually lit,
Yeah, if you wanted to, like I said, I know that they'll be, or that they have a combustion efficiency. It's not just, quantify, but it's actually providing the efficiency numbers of that. And I'd recommend visiting with the Providence team this week. They've got a lot of really good technologies. That's a little outside of our scope of partnership, but they do have that. Are you giving a presentation on that this week? Yep. Yep. Mhm. Yep. Awesome. So I'll get into the unit here for a few minutes just to start, and then we'll take a break. What time is it? 10:30, and we're done here around noon. So get into this to kind of show you. But all I'm doing here is you've got the tablet itself. And again, this is just my tablet. Simply double touch on this thing, just like you would normally use if I'm using a mouse. It's going to open this program. And this is what we've been looking at. Now you'll notice it's a big white screen. I haven't, I'm not connected, so I'm not tethered. I don't have a Q mode file pulled up or anything like that. So this is just a blank slate of what this would look like opening. One of the things in working with Providence that we wanted to do is for situations like this, out with a one-on-one with a customer, or even for your LDAR expert that might have this and be in charge of training internally people. They added this demo feature. All this does is pull up examples from the field that we've got over time. We're more than welcome if you have something that is extremely unique and would be beneficial for us to look at. This is, feel free to send it to us, and we can add it to the demo feature. But we can do all of this at any point in time. I can actually quantify this and see what's happening. As an example, I'm just going to tap the measure button here. I'm going to move over, since we're here in the States, I'm going to change this to standard cubic foot per hour. I'm assuming that's what most of you people in this room are probably used to seeing, just to give you an idea of the size, what a leak would look like. This is one of the ones you've seen. This is the first demo asset, just called just a connector. You'll notice the bar running to the left. This is 43 scuff as far as size go. You'll see that I have all of the overlays set up, the Delta T overlay to ensure that I don't have a Delta T challenge within this video or within this demo example. The Plume overlay, just so I can more easily see what's happening at the exit, at the point release. And then I do have the boundary overlay to see what's recording in the mass or volumetric reading. Another thing on this, with this one you saw earlier, if, for example, I wanted to get rid of certain areas, I could mask out. I'll show you that in a couple of other examples. But running into another, this was a field example that I did just a few weeks ago. Got it, liked it, threw it into the demo file. This is just a flange connected, just a flange connection here. And all these parameters, all these inputs, really easy to see or use. I wouldn't need to come back here, go to standard cubic foot per hour. This is just set it up and measure. Now, if I'm running a Q mode file, which after we take a break, I'll pull up some Q mode file, I'll pull up some examples that are both good and bad. I want to show you the call outs, and I have some tips and tricks on the presentation as we pivot back over to the PowerPoint. But this may have been one that I just threw this into the demo file. But this is, just a standard, didn't like the 37,000 standard cubic centimeters. See if this will do see if it'll do standard cubic foot per hour. This may be something I need to look, because we haven't done a whole lot of adding the Q mode files into the demo assets. So I'll look at that with the Providence team. But really easy to use with various demos. Here's one that would be an example of where you might want to use a mask. Even though you've got the red here and you know that it's going to get rid of it, there are times where the edges might begin to start to look like a leak to it because the camera might be swaying a little bit on a tripod, or that actual mast might be swaying. I could go in here, and if it says mask off, that means that it's off. If it says on, that means it's on. So I'm just going to go counterclockwise, and I'm going to cut out a certain area of that circle, that boundary. You'll notice in doing that, I get rid of this, but the leak doesn't really go there anyway. The leak doesn't cover that part of the piping or the area. And then go back to just using this and doing this. Another thing that is unique about this is that, is this, just curious if anybody's paying attention, is this an emissive or an absorptive plume? This is an emissive, it's a white. And by this means it's a cold background and the plume or the gas is emitting energy into the camera. Absorptive is that it's absorbing the energy and not allowing, and that's the black plume. So this is the emissive plume, easy to see, and you can see right here, just, is it a white plume or is it a black plume? I can change that. Now, if I change that to black plume, what does that do? I'm telling the camera to flip everything. So everything's going to be in delta T, because it's going to, everything's going to be challenging. And when you ever get out in the field and you come back and every video looks like this, 99% of the time, I can tell you from personal experience, you messed up the plume polarity. So, you can run that and be able to easily see what's happening there. The other thing that is unique, and you don't see it often, this is that 5% of the time, when you have a leak that's, forgot what y'all say, larger than 3 inches, or is it 1 inch? As far as the exit area, you would have a diffuse leak because it's a much bigger leak. Even though this is kind of a point release, the point release is the exit area is more than 3 inches in size. Yes, ma'am. Yeah. Yeah. So these are the user data input parameters. So again, you put these in the camera in Q mode or tethered while you're in there, or you can change them here. So the first one, user data, is the polarity, emissive, absorptive plume, all of that. What color is the plume? We've made it simple. We had emissive and absorptive, and it began to get, and they said, why don't we just do white and black? So much easier to understand and to communicate. The leak type is diffused. That's going to either be like a seal leak or something where it doesn't have a single exit point, or if the single exit point is very large, bigger than 2 or 3 inches in diameter, you're going to probably do diffuse. And what that does is that it changes the curve and says, this is a bigger leak. We need to adjust for that. The lens, you'll notice, you can't even see it back there. The lens is already preset by the camera, whether you're tethered or whether you're Q mode. Then you start going into the parameters you would put in. The one is the distance. In this case, we're about 40 feet. I would simply go in and change the distance if I wanted to. What I want to show you real quick while I'm doing these, how these parameters do affect the reading. I'm going to go ahead and run this with the notch filter just to make sure it doesn't get any bad data from the vertical tower. And this is 2,200 standard cubic foot per hour as far as the leak size. Now I'm going to go in here and I'm going to change, I'm going to say I'm a lot further away than I thought. So instead of 40, I'm going to say I'm 58 feet away. Two things, you'll notice that boundary changed. You see how that circle went this big and got much smaller? Because as Yoshi was talking about, now each individual pixel, the size of each individual pixel and how much it fills with that intensity of gas, that size of that pixel changes. And so we need to tell the technology that we're moving further away and adjust for that, because we're looking over, we're measuring as that leak moves over time, over a distance. Now, just to show you, that other one was, I forgot what it was, 5,500, I think. Standard cubic foot per hour, and then you're going to run this. If you're running real recordings and not in demo mode, all of these 2,500. So I believe it was 2,200 a minute ago. So you can see it changed a little bit, not a whole lot. If you're running this outside of demo mode, every number, every recording would lay in here and would show up. Because I'm in the demo mode, it doesn't activate the previous run recordings. So I'm going to go back over to 40. The next one down is temperature. Now, temperature is going to probably be, to be accurate, temperature is probably the most important. As we've talked about, has anybody figured out how many times I've said delta T? We're not doing drinking games here today, but you wouldn't want to play that game with delta T in this. But you want to set that ambient, that temperature. If I were to say, well, the ambient temperature was 100 degrees and not 70, you'll notice two things. One, it changes the amount of delta T, right? It changes what's happening there. But now I'm going to run this, and I would imagine going back to 40, 40 feet in distance. I'm going to run the results here, and that number went from 2200 all the way down to 300 to show you how important the delta T is. And I just changed the delta T by 30 degrees. That's a huge change, and you really need to input your ambient air temperature as accurate as you can when you're out there in the field and utilizing this. So to get back to average, I'm going to go right back to 70 where we were. Composition, again, the intensity of composition, again, it was 2200. I'm going to change that from methane to propane and hit measure. So now what I'm doing is I'm telling this to rerun that algorithm, that big formula that the Providence team has perfected. And I'm telling it to consider that this leak has the intensity, the R factor, the response factor of propane versus methane. And you'll notice how the reading goes down dramatically from, again, 2200 down to 170, because we're telling it has more color. And so methane, it's got to take into consideration that the darkness of it, if it were methane, you've got to multiply it, because methane is not as high of a response factor as propane. But if I tell it it's propane, it's going to take that number down and divide by whatever equation you have there. So that's all of those factors are going, and these are the numbers: propane, methane, propylene, ethylene, ethane, butane, and benzene are the gases that you can use. Now we do have the capacity within Providence to say, well, the main gas I use is something that's a little bit off the wall, to put different R factors and different gases on here. These are just the most common gases that we've seen, at least in an entire stream, either downstream or upstream, that we would see as the predominant gas within that mixture. The wind speed is probably the least important. They're all important, but this one, and you can tell how important it may not be. It's just calm, normal, and high, right? So it's, is it 0 to 1? Is it just a little bit of wind? If you're in Texas, you're never going to get the calm. You're hopefully getting normal most of the time. And then if it's over 10 miles an hour, you just tell it, and that's just telling it that and that's helping to define how fast those pixels move when they're moving from that point released all the way past that boundary. Yes, sir. Well, I believe that they can create, if you know exactly what your composition is. Yoshing, I know that y'all can do a mixture formula drop down and have company X that has X percent of this and X percent of that. I believe y'all have done that before in the past, correct? Correct. Yeah, you can have a customized. I know the QL 100 have that where you can put it in. It's not off the shelf, but we can work with our customers to ensure. Custom one, yeah. So the wind speed is not going to affect it much. Campaign, that's a sexy word for folders. So you go in and you define a folder. It's where you want to save this. In particular, that's mostly important when you're doing this tethered in the field. If you're doing a Q mode, you bring the files and you put it in whatever folder you want. You open it, you run, and that's where it's going to end up. When you're doing this in the field, and what the Providence team, when they did their studies, they called them campaigns. And so where would you put that campaign is test study X or well pad, basin, whatever it is you want to put. So in essence, that's just a file folder structure. And then memo, because this is touchscreen and just like your phone or anything else, I can actually type a memo of what I'm seeing there. So that's kind of those user parameters off to the side. All of those are adjustable before and after. You just have to know what's happening in the field to be able to adjust them appropriately, and to be able to use that.
How important is it to have standard boundary circle?
You want it as centered as you can get. If you have it out of the circle, it will make a huge difference.
Well, let's say.
But if it is not centered, and you're doing this in a mass or volume, it will make a difference. It will still get a reading, Yoshi, but it will be your percentage of error will go up a little bit.
Center, less number of pixels, but each pixel has higher concentration. Remove the circle of the center, each pixel may be gases more. You're going to have a smaller value for each pixel. You're going to have it's mass, yeah, it's the mass constant. It is a factor, but it's not
Huge factor.
critically, yeah. Unless you go way out.
Yeah, this is a connectivity issue with running this through Teams. One thing I'll show you real quick, and then I think it's maybe time to take a second break for the morning. I want to show you the ability to do this, and when there might be a good scenario. Is that running even? A good scenario to do the concentration reading, and one of the unique things, as Yoshing talked about in his presentation point, there is a lot less data needed to do concentration. You're just measuring intensity at an individual pixel. You're not concerned with that moving over a distance, right? You're not concerned with that that mass or volume, that change as the leak is moving. So I'm going to come over here and choose my concentration reading. And so what's happening with the concentration reading is that it chooses the maximum intensity inside that box. At any point in time, it's the maximum intensity of what's happening. Right here, this is a good example of a problem in somewhat of a bad video in some cases, because there is a string hanging from the lock on the pneumatic actuator. You'll notice that string that's showing a leak because the quantification solution doesn't understand that there's a string or a key or a rope or whatever, or an LDAR tag hanging down there, and it just sees something moving. It doesn't know what it is. It just sees something moving back and forth that really kind of looks like a leak. And so what's unique about the reason I choose this one is I can quantify, I can move this wherever. So now I'm going to get rid of the key, and I'm just going to quantify realistically the top half of the screen. And I'm going to quantify this in parts per million meter measurements. There is a huge delay here running this through Teams. But as I quantify this, you're going to get a result of 3580. Now, I don't know exactly where it is, but I bet it's pretty close to this exit corner. I would imagine that if I run it there, I'm probably going to get the same number. because it's still in that big box. It's choosing, in essence, the maximum intensity pixel inside that big box. I may have missed it a little bit now. It's 3320. But if I wanted to quantify, and if you think about this, compared to a sniffer, let's think about the way a sniffer does. You're assuming a sniffer finds the exit point. But what if that sniffer, when it registered the reading, only was sniffing this corner? And this is where it hit, and this is where it actually began to find that reading. This is again 3580, 33 or 3320, whatever that number is, 1250. You can see a pretty dramatic, almost a 3x change, just because of the situational awareness of optical gas imaging through QOGI. That situational awareness to know where the leak is coming from, where to point it, and where to actually measure, where to take that measurement within the technology. And that's a huge advantage. Is getting back to the very beginning slides of my presentation. It's a huge advantage of quantification and the technology that we have. And again, this is a really good example of showing that, as well as a scenario of utilizing the QOGI. And one good thing about if parts per million meter, if concentration is more acceptable or important, it's much easier to use on the field or afterwards. It's just, you just simply put this box wherever you want. If you do have LDAR tags, it is easier in some cases. LDAR tags are one challenge with QOGI. We'll show you some examples in which some people sent us some readings and said, your technology sucks. And we're like, hang on, you got a big tag hanging there that's just moving. If the LDAR tag doesn't ever hit, so if I want to take this one back, one last thing before we jump, go back to standard cubic foot per hour. You'll notice that string or that key hanging, it never touches the ring. That means the technology is never going to take it into account. It's not moving from an area out of an area. So it's going to actually it's going to disqualify, if you will, that for the most part. You still don't want it as much as you can. But if you ever have a foreign object that's touching the boundary and trying to do mass or volume, that's going to be a big challenge with the quantification solution. So when we come back, maybe we'll take a 10-minute break if that works for everybody. I'm going to run through a couple of good and bad examples, and then show you kind of the Q mode, how to load a Q mode file. That is what most operators do, and then take some questions and give you a little bit of input on some field trials that the Providence team and the FLIR team have done over the years. So another 10 minutes, would that work for everybody? Maybe with a 40, 52 after? Right? Yeah. And I'll be here with any questions if you have them.
Go back to the concentration on a square. Are you confident that number down is a delta T, or is it kind of the delta 5 earlier? I'm thinking back to that curve, that graph that you had earlier when you did session. So,
Well,
you get a feeling your delta T is less than 2. Confident in that.
if it's less than 2, you're going to see this whole thing red.
Okay. But
Right.
So in 5 range, is that okay? Yeah, 7.5.
Yeah. So this one right here, well, yeah, I changed this. You notice how bad this concentration reading is because I got the key in there. But in this case, it's telling me that my average is the average delta T within the screen. Is that right?
Okay, so you're not inputting that in.
You're inputting the temperature, and because of the temperature, you ambient air temperature, it's telling you the average delta T in that screen is 6.4. The higher the delta T number, the more stable the results would be.
Yes.
The percentage of error with that huge curve. And if we 2 degrees is just that number where we're confident in that, but there's 2 things. One, on accuracy of this. The 2 things that we've noticed. One, the higher the delta T, the more accurate the reading. The other one, the more aggregate readings you have, the better the technology for accuracy. In other words, if I go out on a 1 basis, say, that's what that leak is, and I say accuracy, stop giving accuracy. The one thing with this technology, it does vary high and low. But if I go take, and these are from field studies of 80 to 100 different scenarios and I go take a basin or a district, or I go to a field study over 80 to 100, that accuracy just goes down dramatically into, realistically, into single and low double digits, as far as the accuracy of the technology. Keeping in mind, we're also an accuracy of the technology and telling it this is where you go. Every other technology is an accuracy. So their accuracy is only accurate in a lab. We're doing accuracy in field tests that nobody else has been able to do because you never knew what to base accuracy on. You're hoping I'm accuracy. We found a leak. Well, how do you know how many you missed? And when we do field studies, which we'll talk about in the QOGI study, when we do field studies against other technologies, like a sniffer, it's pretty dramatic as how inaccurate those are. And they wouldn't even find the leaks, in many cases. And even the Fort Worth study found out that how many leaks did a sniffer miss? Yeah, it's a lot of operator error. There's a lot of misnomers. Like you've asked some questions. We've asked a lot of questions about about compound.
Yeah.
Same thing with a sniffer. Like there's the other technologies. I mean, if I use a sniffer,
It doesn't tell you.
it tells you.
There's something there.
Yeah, it tells you something there, and you get one guess. You get to tell it what one guess. And when you're done, you don't have a spreadsheet that you can input that in and adjust that and change it after the fact.
Oh, that's another question. The whole importing spreadsheets. So let's say, so I'm a regulator. If I have a refinery send me the 4 files or the 3 files that is generated from this,
Yeah.
will I be able to open those up and adjust things if I need to?
If you have.
So I have to have that
Yes,
technology also. Okay, that's a great point to know.
Yeah, you would be able to see the PDF,
But not be able to.
but you would not be able to do that. Just like if somebody sent you a clear image
Yeah.
from a temperature measurement camera. I'd be able to look at it, but I can't move the spot from the center to the top right unless I have a clear software.
Okay, I assumed it was gonna be the same, but wasn't sure. So it's good to know. That's a good point it's a good selling point for my director. Hey, if they send us this, we need this to adjust it, so.
And in reality, if you had operators and you had the technology in their camera had the mode in, they could actually go on a tripod or a mode file, and then, now you're talking a pretty big file. You have to transfer, Dropbox, or whatever. They could actually send it, and then you can analyze.
I thought it didn't look that big for the file when you had it up there. There is kilobytes for, what was it, like 3 or 5 seconds for videos?
Yeah, but the actual SCP file
Is much larger. Okay.
40.
Okay, so if you were to do multiple locations,
Yeah,
it gets really big real fast.
Correct. And again, if you have a zip file, you zip them up and send it over to somebody, but you could process it on a QL, even if you're not with, if just somebody sends you the data. I have customers that have a camera, they have a couple of cameras with Q mode, and then they have somebody in the office that processes the data.
Okay. So it's great information so far. I'm going to stretch the legs into the rest of the report back.
Yeah, I'm gonna do the same. And
Okay, great. So how long have we been? Do you have a rough agenda of what you want to? No, it was not. I was so we do a demo and then we'll have Do you get anything from Darian that shows like a image stuff here? Can you send me that, please? No, no.
Oh, man.
Yeah, I say anything. That's what he's thinking about. I covered it at the start, but distances versus sensitivity and peak size. These, what was the maximum?
Maximum distance quantification that we have in the way it's set up is dependent upon the lens you're using. With our telescopic lens, you're looking at around 100 feet. With the standard lens, I think it's right around 60, around 50 feet, let's just say. Give or take 46, 75, or 100 if you were just put some round numbers on it. Depending upon the field of view.
And it still meets the sensitivity and peak size of the, or the quantification of.
Yeah, we have no defined area, there's no defined area or anything, but what that does is the formula and foundation that they build, those are the optimized distances, because as you move from 1 foot to 2 foot, 3 foot, whatever it is, that formula changes, the curve of that formula changes slightly. And so those are mapped out. And we can add it way out further. And what happens is if I have a circle and my body is a square, it's this big at 5 feet, and it's this big at the maximum distance for that lens and that camera. So it affects it. We adjust for it in the technology. But we did set some kind of maximum parameters, minimum and max parameters, depending on lenses that are just most optimal technology. Filling for John, okay, Yoshi?
This is where we full disclosure, we were with Honeywell.
Yeah, I saw Robert.
This is great.
Were you with Rebellion as well? Or just?
No, I've only been there 6 weeks.
Oh.
I was born in.
Trying to get Robert out of there.
Yeah, exactly. I'm surprised he hasn't retired.
They're making too much money to retire.
Yeah, that's true.
Yeah, see, because it's sitting there, she's sitting in the middle.
Are you still in Kingston? Yeah, I mean, we're at the downtown location, but unrealized. The office manufacturing. So,
Were you at the old Rebellion office down there?
yeah, it's a cool office, but they'll be surrendering that.
I'm surprised it's
Yeah, I agree, yes.
Get that acquisition. Get out of
Yeah,
here.
exactly.
Hey.
Oh, man.
You mean why they received $4 million for ARPA-E to make that device?
Have you heard of Optical project? Was supposed. The original for Rebellion was not for. Yeah.
I just wanted to confirm that from the person who is.
Yeah, Robert was one, but I've been, yeah, sorry. That question came up.
It's not.
We're still trying, but it's not. But that was the original. Hard. I don't want to put a $40,000, $100,000 camera apart. You ever seen a pipe? You ever seen a refinery? Who's done? It's working.
Yeah, I mean,
It's a great residual.
someone needs to keep his head still. He's not gonna be distracted.
Yeah, yeah. I'm not gonna go. But it's also. I think like the insurance, like But it likes a live demo. Give another couple minutes.
Get him off.
Yeah. They're already serving lunch?
Oh, yeah.
I even went back to the presentation.
So it was interesting, the EPA, because next week.
So I tried to, I thought that we did this, it was like, well, you said, all right, I want this thing to start at the 10-second mark, and finish at the 1 minute mark, and you'd be like, all right, just gradually roll on average. That's not. We went, I locked it into each slide text, and then it was literally just a slide, a video with text, all over the whole thing, you know, it was like, I'm not gonna separate 5-second text chunks. That was fun. Did you ever end up doing it?
Yeah, actually, Johnny helped. I recorded that.
You recorded it. What I did was I recorded it, I just set Syria, but I set my phone up and just record audio, put it out, fixing errors, so I had it all typed out. And then all I had to do is, you know, OGI doesn't quite understand what our terminology is. But I just recorded straight through, fixed the errors, and then just chopped it up, so.
Well, I know we lost a few people, but I do want to, in the essence of time, kind of go over, and I appreciate those of you that either have nothing better to do or actually interested in this technology. So one thing, before I get back into the actual operation on the tablet, I like to go over the tips and tricks so that whenever I get into the tablet, show you kind of how it works. And then I can give you, some real video and real life examples of the tips and tricks that we're utilizing on there. As I mentioned before we went off to break, realistically, the number one challenge that I have seen from the input from, what there are people that are LDAR experts that have 10,000 hours behind an OGI FLIR camera, but QOGI is different, right? And they've sent me stuff back and said, this doesn't work. In this case, you'll notice right here, there's a tag in here But you'll notice as the tag moves, it goes from blue, and I don't have, this isn't the video, but the tag crosses that boundary. There's the tag right there that is near the leak area. And so as that tag would move across that boundary, the technology just sees moving pixels. So if I run in, I believe this will run in. So as you can see, the tag will turn blue, green, and this is just saying there's a leak. Now there is a leak up in here. Obviously there's a leak. They got an LDAR tag hanging there. They've already found it, trying to quantify it. But LDAR tags to the QOGI technology can be a bit challenging. I want to say a bit. They are completely challenging, in particular if they ever cross the boundary for a mass or a volume. And reality is this moves everywhere in there. In this case, would be very, it'd be pretty much impossible to quantify because again, the tag looks just like a leak. The other one, tip number 2, this, if you want some of this, you can, yeah. Quick solution of that, yeah, take the tag off.
Just to put bubblegum.
So we need to do, they wouldn't want to know, Yoshing, what we would charge for FLIR branded bubble gum. Exactly. It's going to be green. But stability is a must, right? Tip number 2, because just as a tag moving, if your camera is moving, the stability of the technology, the stability of the detector on a tripod is a must in the way that it's developed today. And so, whether, and one key here is I've had numerous people, regulators, operators send me a video. I'm like, and it really looks like it's still, but then I process it and it's barely moving and they're just leaning up against a truck or leaning up against a pole. I'm like, well, I thought I was still enough. I didn't have a tripod with me. Still enough won't even cut it. You really need this to be on a tripod. Well, you have to have this on a tripod for the technology to operate. This is one sent to me by a regulator saying, man, I really thought that I was still, and it looks pretty still, but you'll notice the size of that leak. It is, nothing's happened. It's just finding, it's assuming that the roof of the building is a leak. You may not be able to see, this is an enormous leak, and this is a pretty healthy distance away, to be able to accurately quantify. But yeah, this is just a good example of kind of still is not quite good enough. I don't know. This is the drinking game. We've mentioned this. Delta T matters. So this is more in a separate short presentation that I've done online. But the Delta T has to be at 2 degrees. We've put some stuff in there with the Delta T compensation. Matters a lot to be able to do that. And this, you've seen this video a couple of times. In this case right here, when the actual reading, this was done out of I won't mention it, but a methane evaluation testing center in the U.S. And so it was the actual reading on a metered valve was 32 liters per minute. If I put the correct delta T, whenever I had the correct delta T in there, I was very, the reading that I had was very minimal in error at 34 liters per minute with the technology. When I changed the delta T and I was off by 2 degrees in the wrong direction, my error went from 2 all the way to 13 liters per minute on a 32 liter per minute reading. So getting that accurate delta T, when I say delta T, getting the accurate ambient air condition, I keep saying air conditioning, the air temperature, getting that accurate ambient air temperature is a key, is very key into the success of the technology. As I mentioned, this isn't maybe the number one importance of the technology, but in particular, when you're doing a point release, when you're doing a 2-inch, 3-inch, and smaller exit emission, and you're using the mass or the volumetric leak rate, getting that in the center is ideal. It's not 100% necessity. It has to be in the circle. I think somebody was asking the question at the break, what happens if it's not in the center? Two things. One, if it's not in the center on the short side, you're really going to have problems doing this. So if this leak is going up, if the exit velocity were right, the exit point was right here, I wouldn't have a whole lot of room to be able to allow the technology and the algorithm to work. If it were off-centered down here, I would probably get a little bit more accurate reading, and more stable to what it would be if it were centered. And so where it is centered matters as well. But reality is we try to, recommend centering on mass and volume. And then we've talked a little bit about the parameter accuracy, making sure what you do out there, all of these things. It is key. This is a good example of how this changes the actual reading. This is a 46 liters per minute leak, or I'm sorry, 60 liter per minute leak right here, measured at that methane evaluation testing center. And when we had the accurate plume, just the plume, you're looking at almost 56 off by 4 liters per minute. But if we did the inverse, and I just was curious what would happen if we had the wrong plume. Well, imagine if you had the wrong plume, but you also had the delta factor, the red background turned off, and you would never know. The reading was 4 liters per minute. So it happens in both directions, up and down. So if I flip that into another scenario where the delta T changes the other way, again, 16 liters per minute. With the black plume, I had 18 liters per minute whenever I had the right polarity. In this case, I had the polarity flipped the other way, right, on a black plume. And again, you're way, way low in the reading, 3.6 liters per minute versus a liter per minute reading. You'll notice all it's doing is it's just seeing a little bit of stuff in the opposite of where the delta T really is running. So what I'm going to do now is I'm going to go back over here. We're going to try this out and see if I can run this out of here. Most ideal way. And if anybody is out there in the world listening to me, I apologize because there's a little bit of a delay there. But what I want to do is I do want to run a couple of these and kind of show you some of the examples. We got into the demo and showed you some of those. But if I go into load, okay, directory is unavailable. So we're going to go into libraries, find my documents. I have my QL320 training videos, and I just had one called Austin. I had some stuff I was working on earlier. To start off, to show you some demo, some demo files of good ones. I believe all three of these are going to be exactly what we've already seen on some of this. This just shows you that I've already actually run this. I've already processed this. So what I'm going to do is I'm actually going to delete this file. So I'm deleting all the data that's in that previously recorded. So once you run a QMode file, it builds that other data. So I'm getting rid of that, and I'm just going to run the SEQ file. That's the FLIR sequence file for operation. Go hit run. Oh, here, run. And now this is going to pull that. You'll notice what I did wrong when I was in the field. Anybody tell me what's wrong with this video? I know you know. Anybody else tell me what's wrong with this video? Let me help you out. Huh? Yep. I had the wrong plume. So I actually put the wrong polarity, wrong plume. I'll run this in standard cubic foot. And so now I pulled this up. This was a QMode file. I brought it from the field, and now I can go process this. there are a few things that you may want to do in the scenario of this. Anybody have any suggestions of what I might be able to do to make this video a little bit better as far as accuracy and reading? Give you a hint. It's called masking. So one thing I could do is cut out the edges of the bottom of that. You'll notice at times where it runs, you get this little blue, this little edge. Now, the Providence team is working on this, and we'll talk about this either tomorrow, I think, on the technology to actually buffer that out. But we, buffer all the maskings immediately out when you're using it live in the field. But you can actually process that out. You'll notice whenever I reran that and I added that mask, whether you noticed or not, you'll notice that this started over with the reading. So the actual results wasn't quite finished running and it started over. So now this leak is 100, is it not going up there? It's 190 standard cubic foot per hour. Unfortunately, the delay from running this through the computer, there you go. 190 standard cubic foot per hour is that reading. So using the Q mode files, it's that easy. Now, if I show you what happens, I'm going to go back to load. You'll notice that I actually, I don't want to do that one. I already did that. I'm going to go to load, and you'll have this DAT file. This is the only thing that the application understands is the DAT file. But if I go in here, a minute ago you saw me delete that. I go to documents. We're going to go, not that one. I think this is the header. These are going to be the 4 files, as I mentioned, that you're going to have. 2 AVI files, the raw video, the Plume Overlay video, the results, which is going to be a PDF file. And then now, instead of SEQ, what they have is a DAT file. DAT stands for data. So in that is all the data that they processed and ran to that Q mode file, but you always still have your SEQ file, which is your original. What's interesting is if I go back to here and rerun this and open the DAT file, it will automatically have the right polarity and have the masking and all of that built in to what we're trying to do. Oh, let me get back into it. And those are, that's how simple it is to go with a an accurate Q mode. But I do want to show you the bad examples. A lot of times in training, it's just as important to kind of give you some of the challenging type of things that you'll see. So I'm going to go back to live training, call it bad examples. And what happens, one of the things that can be a challenge in the technology is clouds. If there's a cloud, keep in mind, it's not always, if it's a huge, just blocked out cloud, that's sometimes not as bad. But if you have a slow moving cloud that's moving at the same speed approximately as a gas leak, as a slow moving gas leak in a low wind condition, that can be a bit of a challenge sometimes to this. So I wanted to kind of show you a cloud example in what you're trying to do here. So this one is running this parameter, and you can see what it's pulling the data and assuming that here's the leak coming out, but it's assuming that the clouds, you can see by the colorized plume, the clouds are a factor of a leak. So when you're using this in the field, you do want to be a bit cognizant of your environmental conditions, a bit aware of the background, because in essence, it's consistently changing that background leak. I believe that this leak was much lower than this 1,500 liters per minute in size, because I think that this was probably, 100 liters per minute, and you're going to have some cloud interference that makes it quite challenging. Even if I were to try to mask out the piping and the tank and those things, it still sees that cloud, in particular when the cloud covers the ring and goes across the ring. Another one is what, this is the black plume. Another one is the same one we looked at here. a little bit different in this recorded video because I have the delta T set a little bit different, but y'all can't see it, but this is pretty much from here to here of a leak. It's a little harder to see on this screen, but there's actually two leaks, a huge leak right here on the vent, and then as well as in the thief hatch on the backside. And so, the reading of this, this is a little probably outside the distance that you would use, but the reading of this is going to be way off because it's not even recognizing the plume itself as a leak because of the movement of other things in the screen. So I mean, it says 5,400 standard liters per minute because it's just finding that building, and as the camera moving. Again, this was a scenario. A guy said, "I really thought I was holding it steady." You're not holding it steady, even if you think you are, and it's one of the call outs of that. And then the last one, this is another example of a moving tag. And so you can see throughout this, I'm going to turn the plume off. You can see the tag just moving around consistently, and it's just going all the way from here all the way up to here. As I turn the plume on, there is a leak there, but the leak is being overtaken by the movement of the tag. And we didn't have any bubble gum at this site, so we couldn't fix it. But yeah, you'll notice that we're doing that. The other issue is even if I change the polarity to white, which is more appropriate to what it is, and rerun this, you're still going to have some of the tag issue as it's floating around in that. So this is a unique thing where you may have a dual polarity where it's polarity where the leak was black, but it actually had some white polarity there. So there may be unique scenarios that you'd have to choose a polarity or another, where it's moving in and out. Yeah, you would have to choose the one that's probably the most predominant in that case. And now it's down like 62 or 23 liters per minute whenever it gets done running here. But yeah, this is a prime example of how that tag really causes some serious challenges in the technology, how it operates, what it does, and the use of the quantification technology for for the QL320. Check one other thing. I believe on my training, Q mode files. Because I don't believe the 4C conference or the Hilton itself would be all that impressed with me setting up a gas emission lab right there. It's really hard for me to show you this technology while tethered in real time and to show you some of those features. And so, we have the tethered technology. The biggest thing, and what I will show you, let's see if I can pull up live. We'll do the stack vent, QL data. Some of the things that I can show you, and this is just a stack vent, pretty big leak out there. Looking at it, standard 1,600 standard cubic foot per hour. But what I can do, it's hard. I don't know if it's going to show you. I can rerun this, and I'm going to change to the manual plume polarity from 7 to 3. And it went from 1,600, and I'll see what it'll run pretty quickly. You'll notice down here, I've changed the plume polarity from 7, which is the standard automated plume polarity, all the way to 3. It didn't change it a whole lot from 1,600 to 1,800 standard cubic foot per hour. I would imagine if I go up to 10, this one, it doesn't matter as much. But you see, as I go up to 10, you start to see a whole lot of interference. Even though this is about as ideal as you can get, 10 is probably a little too sensitive for almost any application. This is about as ideal. There's sky background, not a dang thing in the background. There's not a cloud in the sky, and a huge contrast leak. So as you get up to that super high, but even whenever I ran this at a 10, you're still only off by a little bit. But when you're using this in the field Q mode, in the field, you're gonna have a standard estimated, kind of like the 2 on HSM is going to be the 7 here on our Plume polarity for manual versus automated. Any other questions on this before I go back and talk a little bit about some of the studies that we've done with the QL320? Some public, some we've worked with some operators, and it's more private. Any questions about the operation of the unit, what it does? Where available, we have a FLIR, a booth here. We also have our sales organization that they all have one of these units, our optical gas imaging sales professionals. So feel free, to reach out to us, ask us about, what it's doing, how it works, and we'll work with you guys. Now, I'm going to try to talk about most of these, but there may be a scenario or two that Yoshing may need to correct me on some of the studies that they've done that I wasn't as much involved with. But what I do want to get in is some of these understanding some of the limitations that we talked about. Delta T distance, and this is a reason I want to pull this up. This question has come up a couple of times. What is the distance? We have it, I said 100 feet, 210 feet. So it's 54, almost 100, and then almost 200 feet with that. So if you have a 6-degree FOV lens or a 92 millimeter lens, for those of you that talk millimeters and not field of view, if you have that, you have this, you'll notice the minimum is pretty much the minimum. It's about double the minimum focus distance of the camera itself in that scenario. And so you can get up to 210 feet as far as measurements with the highest in lens, up to a little over 50 feet for the most common lens on the cameras. Another common question is, what's the max leak detection? What's the minimum and the maximum that we can detect? That will depend on the two different calibrations. As Yoshing talked about, we have the calibration curves that are built into the equation, and they're built into that equation, and they're part of adjusting the way the technology works, depending on that input of distance. So if we look at that, there are two different calibration curves from the 10 foot and the 30 foot, and these are with the standard lens. So the maximum, you're going to get it with a diffuse, that diffuses a large 10-inch. I thought I was saying 2 inches. I thought it was 10-inch release geometry. So a big, huge pipe, something like that, something that is not directly out of a point, up to, with methane, up to a 300 liters per minute, as far as the maximum type of leak size that you can get. Now, those of you that say, there's other technologies like a high flow sampler, which is pretty common in the technologies. I don't remember how many factors lower it is than this, but there are extreme limitations, and it's another huge advantage of the QOGI technology is the breadth of actual leak detection, minimum and maximum, that you can use with the technology. We talked a little bit about this doing the live. Understanding the conditions is unique, and understanding what's happening from a white plume to a black plume, same thing. And so if you have those conditions with a cloud, it's going to always be challenging to utilize the technology and be able to get accurate readings there. And as I mentioned, the Providence team, as well as FLIR, this thing in here. We've done a fair amount together. I've done a fair amount of studies, some of them a bit more recent. And I'm gonna highlight 3 of the studies that are probably the most prominent because they're public. These are all the studies that are out that we have within the technology. But I'm going to highlight a few of them. So you can see that the team, in particular the Providence team, they've been very aggressive in getting feedback from the field, getting feedback from operators and users to make sure that the technology meets the demands of the industry. One of the first studies that Providence did, this was actually, and one thing to note is this study was done with a QL100. This was the first generation technology, and this was done over with an organization called Concalway, which is out of Europe. And they're a leading environmental science type of evaluation. What they do is evaluate these types of technologies. So Concalway did this study out of Belgium. And so when I say you need to understand this, the QL100, we've made dramatic advancements in the technology from the QL100 to the QL320 to the FLIR QL320. We've all learned a lot on how to make this be more accurate, more user-friendly, and be a better technology. And I don't know the increase in accuracy from now to then. We looked at, leak rates up to 1,000 grams per hour, a variety of backgrounds with respect to this, and they did quantify 3 primary gases as well as, did you have a mixture preset? I don't remember whether John had a mixture. I believe he may have like a mixture preset into the camera of 33% of each of those. This is a public study. One thing is unique. I mean, you can go online, read this whole thing. I don't remember how many pages it is. It's a very informative study. This was actually done testing directly against a sniffer, because at the time in 2006 and even today, how does this work against the technology that people understand? Keeping in mind that they had to, do a factor-based calculation for reading with a sniffer. But the breakaway or the takeaway from the study is, if you look at the average, we see that there's going to be errors here and there, but if you just look at the average compared, and this was, I believe this was a directed study, and what I mean by that is we were telling the sniffer where to go. It wasn't blindly saying, here's a room, go find a leak. You want to take an OGI camera against a sniffer in a room this size and say, find a leak, we'll win that every day. Unless it's super, super small. But we would tell the sniffer where to go and measure it. There were scenarios that they had extreme trouble even telling them the leak is right around there. I don't know if they used the camera to point it, but they would say this is where the leak was. So it wasn't a complete blind test, but the average standard deviation, the average error for the quantified QL100, the QOGI technology, was 6%. And under a 10% error is super impressive. This is also done, again, in conjunction with a third party. I will make the statement that the Providence team was there to support the technology, but it was completely, but so was the owners of the other technology there to do their part in the study. Whereas the average error of a method 21 TVA or sniffer, the average error there was 31%. So you're looking at an over 5 times better accuracy to the gold star in downstream regulations as far as quantification goes. So this is really, really unique with that. A couple of these other studies are a little bit more in the, I may blow through some of these on the essence of time, but some of these were more with, you'll notice a campaign in upstream oil and gas. Some of these studies were with partners that were interested in understanding, interested in advancing quantification technologies within their testing. And so this one was in upstream. It was upstream and midstream. Completely blind testing, leak rates from 0.4 liters per minute. So extremely small leak rates, and so. This was tested against a high flow sample. I don't have the results for that one. One thing that was unique, there was a NPL testing, and the reason I show this one, sometimes when we do these studies, we find errors in our technology, and this is one reason we really like doing this. Error may be a bad word, but you sometimes find scenarios in which you do this. This was a study in which I think that there were 6 to 10 optical gas imaging technologies that participated. The Providence team was the only team that submitted the results to National Physical Laboratory in the UK. They didn't have enough results from anybody else to be able to publish this study. But what we did learn from this study, is, one, the high leak rates. We really could do a lot of this. But what we learned from the study was it helped us in understanding that point versus a point release versus a diffuse release, and make our technology better for what we defined as pooling. And what we mean by that, where the leak stays in this circle and just kind of moves around. So you'll notice the exit velocity here kind of went down, and then it came back up, and it pooled, and it had a little bit of trouble. So really unique on this study is that we were able to advance our technology, make it better by some of the learnings that we got in participating in a study like this. If we were to take out the average of error in full is 46%. But if we understand more of, as we did this study, that, the pooling effect in extremely low wind scenarios. Now, again, most of you that do upstream oil and gas, you're never going to have to worry about the low wind scenario. But we run into that. We had an error rate of 15%, which is really good. This is error rates in the magnitude of a high flow sampler of bagging and taping it up, getting it set up, and taking complete and total accurate readings with a high flow sampler. This is in that comparative rate. And so really good performance at that testing. There was another testing up in Canada, independent testing up in Canada, a little bit smaller, Saskatchewan Research Council, SRC. They were just more doing an evaluation testing and doing this. This is available online. The accuracy here for this overall testing was right at 30%. And the bigger the leak, bigger the delta T, the better the accuracy. So this was a really small leak type of analysis, which the accuracy of the smaller the leak would be a little bit more challenging. A newer study that was published in June of last year was unique because we were not involved in any way. We had there's a gentleman out of Harrisburg University who is dedicated to, I don't know how many years, but the majority of his scholarly life to evaluating methane detection technologies. And they performed the study. They used the device, and they did everything on their own. This was a two-part study. The first part of the study was to evaluate new technologies, and they needed a baseline technology. So what they wanted to use for baseline technologies is understanding and evaluating the QL320 as well during this. So keep in mind, this has nothing to do with us, and to be the gentleman running this is somebody that is very, very critical of technology, as he should be in his position. And some of the outcomes of this to us were a bit surprising in what we're able to do. In summary of this, it was I believe it's over 100 tests, about 100 tests. And again, the report link, it's PTAC, Petroleum Technology Alliance in Canada. But the summary of this was that on an individual basis, their analysis was that the QOGI technology is ideal, is less ideal on a one-off basis. But the more aggregate data you have, the larger the sample set, and that can either be over a study. It could be over a basin. So if I go out to a well pad and take one reading, the accuracy error is going to be wider than if I am aggregating my readings over this. Where does that come into play? I think the gentleman somebody may have asked earlier about the potential of this for inventory, emissions inventory. The larger your aggregate data set, the more accurate the technology it gets, according to the scholarly expert on methane mitigation that ran this study. We had an aggregate error over the study at 18%. Over the previous years of studies, in general, the high flow sampler, which is many people still say is the gold star for mass and volumetric measurement, but quite cumbersome to use, has an average error of around 10%. We're really getting close and getting the technology really close to this, even with third-party analysis. The other thing, we've talked a little bit about the thing that a high-flow sampler has a maximum standard cubic foot per hour capacity up to about 500. Whereas our technology can get you up to over about 3,000 standard cubic foot per hour as far as a maximum reading. So we really expand that offering, and to do this doesn't even mention the fact that there were components on there that a high flow couldn't have got to, would not have been able to access and be able to be able to measure because of the difficult to measure opportunities. What we decided to do after seeing this is we went out to that methane evaluation technology center, and we did our own study of almost 100 readings at the METEC facility. So we went out there for 3 days, just taking data point after data point to evaluate all of our FLIR technologies. We had a man lift, so we could take all kinds of different angles of using a QL320, even though generally it's probably going to be used from the ground. So we were able to just store a bunch in, because we had the Q mode feature. We would just, every single emission that they set up, just set it up in Q mode. So we had about 80 studies, 80 evaluation data set samples. What was really interesting about this is when we got there, so we were there, I believe, 3 days, like Tuesday through Thursday. First day we were there, it was 31, 32 degrees, cloudy, nasty, to some degree, a little bit of a mist. And by the time we left, it was 70 degrees, beautiful Colorado day, 70 degrees. And so we really were able to strike, really do a good job, and got lucky by getting a huge variety of data sets for environmental conditions from the entire facility. The results that we had were very similar to the Alberta Methane Field Challenge. With that, we wanted to see if we did our own studies on an individual basis. We saw the same thing on an individual one reading basis. The error is going to get out there, but the consistency of the technology, it's not, everything's off by one way. And so as you have more data sets, as you have more information to be able to pull this in, we had an average aggregate error of 4% in this study. And again, this was us doing the study, so probably a little bit more expertise in evaluating this than maybe a brand new user of QL320 or of QOGI technology. The full aggregate, the actual leaks from the METEC, we had the METEC facility. They were the ones running. They were the ones keeping the numbers and the blind tests. They just gave us a spreadsheet after and said, hey, here's test 1. This was the leak rate. Here's test 2. And then we filled in and did all the information on our own. 3151 liters per minute over the full study. We were at 3281. I mean, it's really impressive in our opinion. And the goal here was to help internally confirm this. And this is something that we have the data on. The AMS, the Alberta Methane Field Challenge, that's publicly available on the PTAC website. The Concolway study is publicly available on the Concolway study. And then lastly, I just to kind of wrap things up, go over some additional resources that we do have available. If you have others in this, I don't know if this is going to be recorded and replayed if somebody wants to listen to me banter on for 4 hours. But we do have, we have everything from the actual product page. For those of you that may be interested or may have people in your organization interested, we did a bunch of subset top feature based under 3-minute videos at FLIR.com/QL320 training. Really easy to use, about 10 or 15 videos that just on the top features of how we're doing this. We talked a little bit about the quick start guide. If you go to our website, we have some different trainings. I did this exact training with our organization as well as all of the partners we have in the entire globe. It's a bit chopped up because there were a lot of questions from partners and FLIR people that I try to chop out of it. But in essence, it's the live training recorded. You hear me banter. It's about a little over 2 hours. That's available online as well, and you can pretty much watch that or share that if they wanted to look at that. And then if you're just kind of interested in learning about the technology or maybe helping share, there's 2 really good papers we have. One is the Understanding QOGI, right? It's really taking everything that Yoshing and I've talked about, putting it into a 3-page paper, and just trying to dilute that down and educate on a very, very 40,000 foot level of what QOGI is. But a lot of the way to answer questions or, a lot of those support technologies is to have that question and answer site, have Q&As. And so we do have a top 10 questions. And this is just over the years, 5 years that Yoshing and the Providence team and then the FLIR team, since we've been involved, just the questions we get from you and your constituents out in the field that say, hey, what does this technology do? This is just a sample of the training videos, different sections. I think this is an example of a video. I don't know if it'll play or not. Yeah, it's not going to play on this setup that I have going here. The top 10 questions. These are the questions that we have on the top 10 questions. Really just simple, basic white paper. Some of the questions that we've had here. Somebody asked about regulatory. Currently uses regulatory. Has it been vetted? The different streams, multiple streams, the compounds, minimum and maximum leak size, the minimum and maximum distances that you can use the technology. So again, it's all right there on our website. Outside of that, do you have any questions? I may have given you back 15 minutes, and I want to say I appreciate the time. I appreciate y'all sitting in here and your time's valuable, and you have choices to make here at this show, especially as much rich content as they have here at the 4C. So thank you for the time, and feel free to reach out to myself. I know that Yoshing or his partner John Morris can help you out, and we thank you and look forward to potentially working for you and with you. We have a full optical gas imaging leadership sales team. They'll be here this week. Right now, they're in an internal sales meeting. They make me go do all the hard work and they go have fun. But yeah, they'll be here this week, and so we can help you out, your colleagues, or anybody you want. So, are there any questions on the technology or close? Anything in particular? Awesome. Well, thank you very much. Thanks for your time. We'll be around if you think of something in the next couple of days. As far as Yoshing and I have a presentation this afternoon. Grab this real quick in case you're interested in some shameless plugs. I have one this afternoon. Yoshing and his team, they've been working with us on an autonomous optical gas imaging solution looking to get field results and trying to share kind of our vision on continuous and autonomous optical gas imaging this afternoon. I also have a presentation. A presentation tomorrow afternoon on this technology, on some of the work that we're doing on the next gen and what we're going to put into the technology in the very near future. A lot of this that we're working with the Providence team, and they're on the precipice of having it available to go in this, but to talk to you a little bit about what are the next steps for QOGI and some of the features that we're going to look at adding, and even some of you there may be some duplicative stuff for what y'all saw here today, like some of the studies that some people may and may not have done. So I have that tomorrow afternoon. And would you know when you're Yoshing, when is your Mantis presentation? So the Providence team, they have a 3-tiered. They have 3 tiers for their organization, and FLIR in our partnership, we partnered with the 2 specific optical gas imaging tiers. one of those being quantification. And Providence, you'll see in my presentation this afternoon, they had an autonomous continuous fixed mount solution in 2008. Is that right? Around 2007, 2009. They had the very first, alarming continuous monitoring solution. You'll see a video of the customer using it in the field. And so those are the two pieces that they have. A third tier called a flare efficiency, which is outside of the realm of true infrared. It is infrared technology, which we'll get into. But he has they have a solution for flare combustion efficiency, really top of the line, to where you can replace millions of dollars of technology with their one top end solution. That's hundreds of thousands. But if you look at the comparison, what time is yours tomorrow?
By default, your emission is going to go with your building. Reality. Yeah, so he'll be in the flares and combustion track, which would be room 406 tomorrow. So feel free to add, and they will be here. They're partnered with us in the exhibit, not hall, but the exhibit hallway. We I don't know if we got advantaged or kicked out. So, but thanks for your time, and we'll be around to answer any questions you have. Oh, sorry? It's at 1:30, same time as my one today. Yeah, it is at 1:45 in the Eldar room, which is that this guy? Yeah, right here at 1:45. Today, I will be next door this afternoon. The OGI room. My favorite. I was trying to see it in record. Is it closed?